Sure. Thanks for coming today. It's nice to see a good turnout here. Just to make sure we're all in the right spot, we are here to talk about storage tanks and air quality and emission calculations. So hopefully that is what you're here for. I mean, we're all here to enjoy Austin and have a little bit of a break from, where we're from, but perhaps we can enjoy tanks for a moment too. So that being said, I am Al Reich. I'm a senior chemical engineer with Barr Engineering Company. I'm out of our Duluth, Minnesota office. I have about 10 years or 10 plus years of experience doing air quality, permitting, and compliance work, really centered in the midstream and downstream industries with a particular focus on storage tanks, terminals, refineries, petrochemical, oil and gas, all that fun stuff, with, like I said, an emphasis on storage tanks. And I've been serving our clients throughout the Midwest and out east for the last 10 years from Duluth. So that is the quick info on me, just to help kind of dial in what I talk about, since this can be a pretty broad topic. If we could just do a quick snake around the room. Who you are, where do you work, what type of facilities, how many years of experience do you have with tanks or air quality? Do you do emission calculations? Is there anything that you're particularly interested in? Just a quick couple seconds, and maybe we can start with you and just kind of snake back through there. Okay.
2 months, under 2 months. I do have a tank program.
Okay.
So just here to learn.
Excellent. Good.
Lindsay, I'm with the TCQ Emissions Inventory team. So we might enjoy your facilities per se, but we do double check, back check, and take a look at the emissions calculations that other facilities like sending to us. Really nothing else to say with that.
I second that. Everything but the name. My name is Jack and Laura. We're here in the Austin area, so we work for the and we both started a year. Well, I started a year ago at TCQ.
Excellent. Oh, yeah, start. Go back.
My name is Chloe. I work at a polystyrene manufacturing play. I have a little over 2 years of environmental experience. I'm responsible.
Reich, Westlake Chemical in Geismar, which is close to Baton Rouge, Louisiana.
Work for West Plastics. Worked there about 5 years.
Okay.
Not responsible for calculations, just to learn more.
Sure.
Everything goes into it, and if there's changes, things.
Sure.
My name is Winnie Dodson. I work for in Houston area and too many years of experience. That takes relatively new to the program, so I'm interested about that. So
sure.
Best practice.
Okay, awesome.
I'm Brett Mattingly. I work for Holly Frontier in Tulsa. I've got about 10 years of environmental experience, but I've only been building the tanks for about a year.
Sure.
Yeah, go ahead. Dina Galloway, Chevron Phillips in the Houston area. About 6 years, 7 years, experience in taking issues, sophisticated, basically.
Sure. Awesome.
Courtney Covington, I work for Eastman in Longview, East Texas area, and I've been in our environmental for a little over 3 years now. And I do have tanks and tank calculations. So yeah, just learning more.
Awesome. Well, great. Everybody is in the correct spot, and I think this hopefully, will cover a wide variety of things. We have just half a day, so this is certainly condensed, but hopefully has enough detail across all the different avenues that we're looking at here to provide some value, help inform and educate, and give you some ideas to take back home and expound upon. So we'll start with kind of the review of the regulatory programs that govern, surround, and impact our storage tanks. We'll talk about storage tank design and deck fittings. We'll dive into the calculations and emission pathways. Talk about some permitting and compliance topics, best practices, et cetera. And then to kind of close it out too, on the Barr side, we have developed a replacement for Tanks 409, a spreadsheet-based tool to do the latest and greatest AP42 calculations. And we have that as a resource available to folks if it's something they're interested in. So we'll touch on that quick. So we'll get started, we'll dive in, we'll get the regulatory stuff out of the way first. And that kind of helps build the foundation for why tanks are designed the way that they are and influences the emission calculations as well. So the fun starting point is, right, are we talking about a tank or a vessel? And what does that mean? As much of a lay definition or as much of synonyms as they may be, that can have some pretty significant ramifications regarding the regulatory applicability of programs. So we'll get into some of those, but it's just important to always read the definitions, understand your regulatory programs, and look for those exemptions. And if it looks like a tank and smells like a tank, it might not be a tank though. If it's a pressure tank or a frac tank. Frac tanks are always kind of a fun one. Maybe not fun, but frac tanks are always curious because they are not subject to NSPS KB because they have wheels, and as long as you don't leave them in place for 12 months, they're not a stationary source. However, depending on your facility operation and activities, those emissions you can't not account for either. So you may not have a regulatory burden for your frac tanks, but it's still important to understand what those emissions are and what they're being used for. So anyway, we should always be thinking about, is what we're talking about covered by these regulations, number one, because that sort of is the on-ramp to understanding if there's applicability or not. Here we go. So from the federal perspective, the rules that cover storage tanks create a very messy Venn diagram. If we look at sort of the different sectors that we all seem to operate in, I think we've got a pretty good representation across the board. There's overlap between terminals, renewable fuels, chemical manufacturing, and refineries, particularly in the NSPS perspective, because that's talking about tank based on size, construction date, and vapor pressure. And some of the other chemical manufacturing rules, but then there are some terminal specific rules that deal with a little more of the loading operations, and some other rules that have more specific refinery impacts for benzene or refinery MAC rules and things like that. But suffice it to say, tank regulations aren't complex at face value, but as you begin to have overlapping regulatory applicability, there can be the need to understand what are your overlap provisions, are there exemptions for being subject to one program or another. So again, applicability may not be hard for a single program, but it's important to understand where your coverage lies across all applicable potential regulations. So that being said, from the most common perspective, I think when we think about storage tanks, tends to be NSPS KB. That's broadly the most applicable standard and does a pretty good job of walking through the standard regulatory requirements for floating or storage tanks and tanks in general. We'll use KB as kind of a guiding standard to talk through inspections, record keeping, reporting, things like that throughout the presentation here today. But KB is not the only rule that has potential storage tank requirements or standards. Again, there's rules for asphalt processing plants. Triple Q for refinery wastewater systems has tank requirements. Quad O and Quad OA have tank standards. Under the NESHAPs, there's other rules as well that have overlap or potentially point to or reference NSPS KB as well. So again, a lot of alphabet soup for those that are a little bit newer to the tank regs or things like that. But it's important to understand, whether you can start with your permits or other applicability documents and see that it's not just one rule that has potential tank coverage or impacts. So that was NSPS, NESHAP. On the MAC side, we have a number of other rules as well that potentially cover tanks or directly point to MAC WW for floating roof storage tank controls, or SS for the closed vent systems. Again, laundry list of programs that have relative applicability. At the end of the day, a lot of the requirements and standards are similar. Again, we're going to be inspecting our floating roof tank rim seals. We're going to be monitoring or keeping track of true vapor pressure to make sure we're not exceeding the standard to require a closed vent system. There are various other inspections, record keeping, things like that. But they all kind of have a little bit different flavor depending on where they fall and kind of when the rules were written. And of course, that was all just to talk about the federal level regulations. We can then dive a layer further into our state-specific rules. And I am from Minnesota, but that's to say Minnesota's air regulations for tanks have a lot of overlap with surrounding states, but there's also a lot of differences as well. And what we see often isn't completely wildly wholly different regulations, but there's some very unique things in different state regs. So let's see, do we have a couple examples of that? So a couple examples. Illinois has a specific standard for vapor pressure representations for tanks that aren't subject to KB to be less than 12.5 psi at a 70-degree reference temperature or something to that effect. So there's a little bit of a lesser standard for tanks that aren't subject to the federal rules. Other states like Indiana requires your tanks to be painted white. Wisconsin also requires your tanks to be painted white. None of the federal rules have specific paint related provisions, but those all exist. And again, this is just a snapshot to, again, not scare, but inform everyone that, especially if you've got jurisdictions across the country, a lot of your tank stuff may be the same, but there are going to be a handful of nuances that you may not expect or may not be aware of at first. So again, just providing some context and awareness. So that being said, whether we're talking federal or state regulations, there's kind of a general structure that everything usually follows, maybe a little bit reordered differently, but we usually see the applicability basis, the definitions and exemptions or exceptions up front. That kind of, again, gives us an understanding, are our vessels, our tanks, equipment subject to these rules? And then if they are, what type of standards do we have in place? Are there work practice standards, which we typically see for storage vessels? It's a lot more difficult to deal with a pound per hour emission limit on a tank than it is for a process heater or stack or something like that. We do see there are instances where tanks may have an annual or monthly emission limits, but more often, at least from the, that tends to fall out in permitting. Typically from the regulatory side of things, we see things, the standards are work practice standards around maintaining a tank, using good air pollution control, quality practices, minimizing, floating roof landing events, things like that. And then we've got some testing, monitoring, record keeping, reporting. This is the pretty standard regulatory structure for any given rule, and we'll kind of dive in and talk about tanks specifically. So again, we'll start with KB as a basis. This is a good one because it has some interesting caveats as well. From an NSPS perspective, we're typically talking about specific pieces of equipment as opposed to whole industry segments like a MAFT rule or some of the other rules. So for KB, for example, our general applicability requirements are based off of when the tank was constructed, modified, or reconstructed, and the size. So then non-applicable tanks would be, there are certain ones that if they're within a certain size range and storing less than a certain vapor pressure or greater than a certain size, slightly different vapor pressure threshold, don't have the same or general applicability requirements as those primary tanks. And then KB also has a number of exemptions for pressure vessels, mobile tanks like our frac tanks, and a number of other things based on the text in the rule there. So there's a handful of other exemptions that exist, but again, it's important to understand as we get started what fits in the box and what doesn't. So the number that we'll talk about a lot, whether we're talking about KB or MACWW, is 11.1 psi for the true vapor pressure threshold. So if our tanks are below 11.1 psi, we don't need a floating roof, or I'm sorry, we can get by with a floating roof as the primary form of control. If we have tanks that exceed that 11.1 psi threshold, that becomes a situation where we need to install a closed vent system and have a control device. So under KB, if we fall into that area where we have high vapor pressures, there's some additional requirements. The MAPT SS has a pretty good example that covers this in a little more detail, where you have to submit design plans, there has to be some testing, there's operating standards for the closed vent system and control requirement, additional record keeping, notifications, and reporting as well for that control equipment. So if you can stay under 11.1 PSI, that really creates typically the more straightforward operating scenarios when you don't have to deal with those control devices. So some other sources of tank requirements beyond the state and federal regulations may be your existing air permits. There may be BACT limits that you take on as part of a project to limit or reduce emissions to stay under certain significant thresholds, or simply as part of your BACT analysis, you have some additional limits or requirements for your tanks for control equipment or things like that that may be above and beyond your rules. A few decades back, the Storage Tank Emission Reduction Partnership Program came into effect to help address the issue with slotted gauge poles and the issue with the 1/8 inch gap criteria. So that had some voluntary agreements to help control slotted gauge poles or guide poles. And that might be what's driving you to have additional controls on a tank that might not be otherwise subject to a specific standard. So another interesting change in regulation or note more recently, last year, 2 years ago, the EPA published a revision to NSPS KB. They provided an alternative compliance option for folks that are subject to NSPS KB to elect to comply with MACT WW. And that is of significant value. We'll get into the inspections here in a minute, but just this kind of tees it up. MACT WW specifically allows you to do your 10-year internal floating roof inspections when the tank is in service. KB was historically vague on the allowance for those 10-year inspections if you could do them in service, or if you had to take the tank out of service to purely do a specific environmental inspection. When the rules were written, there was more alignment between API integrity schedules and these environmental inspections. However, with developments on the API side and the ability to keep, from an integrity perspective, internal floating roof tanks in service longer, there's been some kind of discontinuity between needing to take IFRTs out of service every 10 years, except for these environmental inspections. So historically, some companies, some of you may have an AMP that allowed you to do your in-service or your IFRT 10-year inspections in service. The EPA issued those for a number of years, and then in the last 5 or 6 years kind of stopped doing it. There was some concerns around how they interpreted 1/8 inch gap criteria for deck fittings or rim seals. And there was some misalignment in different regions issuing these AMPs. So the EPA stopped doing that for a number of years. And then in 2019, they published the alternative option in KB. So that allows us to comply with WW, do these inspections in service. The challenge is that it's pretty easy to utilize the alternative compliance provision. It's a 30-day notification. There's some additional record keeping retention requirements. There's a few deck fitting control differences around stub drains and other things, and your automatic gauge float wells need to be bolted and gasketed or mechanically fastened and gasketed. But the challenge is, this is, I think, a generally positive for the industry. But if you have internal floating roof tanks that are subject to KB and you have not yet thought about this or doing the inspections in service, it's an appealing compliance strategy, but doing an internal IFRT tank inspection when the tank is in service provides a pretty significant safety and logistical challenge to get a crew in there to do these inspections. So if you haven't thought about it, it'd be a great opportunity to have a discussion with your tank inspection group on scheduling, but it also may not be the silver bullet that everybody wants, because getting a crew inside of an IFRT that's in service is a relatively complex safety maneuver. So it's good good tool to have in the toolbox, but may not be the ultimate solution that folks hope it to be for the in-service situation here. Oh, so speaking of inspections, that unique caveat aside, we'll start kind of talking through some of these inspection requirements that our tanks are subject to here. So we'll start again with kind of covering what we look at from an internal float and roof perspective. Typically, we have the annual inspection from the gaugers platform. This is just a straightforward inspection from the platform. A visual inspection: is there product on the roof? Is there appreciably noticeable visible damage to the seals, the rim seals? Is an access hatch lid missing? Is there significant product on the roof? Is there something else that has failed or appreciably, very visibly wrong with the tank? And those have to be, if there's failures, have to be reported and repaired or fixed within 45 days. I already spent some time covering the complete out-of-service inspection that's required every 10 years. Again, under KB, it must be completed out of service. However, we now have this alternative compliance option that may be a good fit for certain facilities, depending on their safety plans and procedures. And MAC WW, if you have a refinery and are subject to MAC CC and ultimately MAC WW, you now have the coverage to do that in service as is. So common failures or common issues that we see with these out of service inspections or the 10-year inspections. You may have deck fittings that don't have the necessary controls. You're missing gaskets, wipers, or other required controls, or they may have deteriorated or worn out that need to be then fixed and replaced before the tank goes back into service. You have to fix and repair them before they return to service. There aren't any reporting requirements for the out of service inspection as it is. If we begin to do them in service, though, then we end up with a similar report your issues and fix them within 45 days, or have to take the tank out of service. Certain tanks, depending on their rim seal configuration, may require these inspections on a 5-year basis, but most of the internal float and roof tanks that I'm familiar with typically have the mechanical shoe configuration and are indeed on the 10-year schedule. So then shifting to the EFRT perspective, we don't have to measure seal gaps on covered float and roof tanks, but for external float and roof tanks, we do measure on a 5-year basis for the primary rim seals, and on an annual basis, the secondary seals, measuring for gaps that exceed certain criteria based on the tank size and diameter. So typically, right, the main issue here is there's a seal gap exceedance. So there's the teams that are doing these inspections have different sized dowels or rods. They go around checking for gaps at 1/8 inch intervals. And so there can be some concerns with is the tank, is this a irregularity in tank diameter, and it's created based on the tank size, and this issue won't exist at a different liquid level. Do you need to remeasure seal gap failures following the repair at the same tank level as the initial failure was identified? And those are all sort of risk-based questions that our clients have different levels of risk exposure to, right? Typically, if we see a gap or an issue, we want to have that fixed, flag that as an issue, have that repaired. And then the remeasuring of the level can be a little bit of a challenge depending on the timing of that repair and when and where the tank is moving. So just some things to consider as you evaluate or look into your facility's seal gap measurement program. And then, of course, beyond gaps in the seal, if there are rips, tears, holes, or other just obvious physical damage to the closure device that's supposed to be sealing off the vapor space from the atmosphere, that will certainly be an issue as well. And again, for these types of failures, there's a 30-day report notification, and then you have to repair them within 45 days as well. Unlike the IFRTs, we have a requirement to do a complete out-of-service inspection anytime this type of a tank or vessel is emptied and degassed. So this is that same inspection criteria as the 10-year IFRT inspection, but for EFRTs, we have the luxury of being able to do it only whenever the tank is emptied and degassed. There's not a corresponding time scale with that one. So again, deck fittings not meeting the design criteria, Another common one we see here is there's not a sleeve or appropriate control on those slotted gauge poles or guide poles. Oftentimes too, wipers and gaskets will deteriorate over time. They get repaired as part of the API 653 process. And again, have to make the corrections before refilling with volatile organic liquids. And there aren't specific reporting requirements here as well. So then what do we do if we have inspections, if changing products stored in the tank? So if we're talking about things from a refinery perspective and you're potentially changing something from a high volatility material that would keep you as a Group 1 storage vessel under a MACT rule, and you're changing to a diesel fuel or something that's a lower RVP and may not have the same requirements, you may, from a federal rule perspective, be in the clear, but if your air permit still says thou shalt do these inspections for this type of a tank, even if the material has changed, you still may need to conduct those inspections because they're in your air permit. Again, there's sort of a hierarchy, right, of air program compliance needs. And one is there a federal rule that says I have to do it, whether it's in the permit or not? Is there a state rule that says I have to do it, whether it's in the permit or not? Is it in my permit, whether or not it's in a state or federal rule? Then I absolutely have to do it because it's spelled out in my permit that says I have to do it. And if you don't want to do it anymore and there's not a federal or state regulation, then you have to get your permit changed to make it go away. And that's why the air permitting world is complex and challenging, because there are 17 different things to keep track of regarding, do I have to do this inspection? So anyway, again, just some context around if your tank is changing service to a less regulated style or type, you may want to just keep everything running as is. But if you're free from permit conditions and other regulatory program requirements, then if you're storing material that is not as volatile, you could then continue to move forward with that new approach. Okay, so we talked about inspections. We'll jump into monitoring and record keeping for tanks. It's pretty straightforward. The big one is understanding what your tanks are and then what the changes are to them if those changes occur. So KB specifically requires that you maintain records showing the dimension of the vessel and analysis of the capacity of the storage vessel. You need to know what you're storing in there, what the period of storage is, and what the maximum true vapor pressure is during that respective storage period. So again, we want to know how big they are for applicability purposes and when they were built and are they designed correctly. What is in the tank to do that maximum true vapor pressure test to understand, do I need a closed vent system and control device? If that vapor pressure is going to change and exceed a threshold, you got 30 days to notify the administrator, and then potentially, depending on what that vapor pressure change is, you'll then need to look into those potential additional requirements that may exist. And then for KB purposes, record retention is typically for 2 years. But in the case of dimension of the storage vessels and things like that, those are for the life of the equipment. So again, true vapor pressure is going to be a pretty significant concept, both from the regulatory side thing here, and then as we move into the emission calculations as well. And there's a couple different categories or approaches to consider when we're talking about true vapor pressure. For crude oils, typically, historically, we've relied on RVP data and the API nomographs to get from RVP to our true vapor pressure. Other liquids, whether it's a pure chemical or things like that, there's standard reference texts for that vapor pressure data. There's a host of ASTM methods for refined products. The regulations allow us to use different methods and techniques approved by the administrator. It's kind of the catch-all for newer and better technologies or tests. A caveat there is, if there is a new standard that may not be widely adopted or is still very new, it's never a bad strategy to approach your regulators to say, hey, this is a new method we are going to use. It is better because of XYZ, or it's more efficient because of ABC. And just make sure that there's not any concerns, because again, with tanks, vapor pressure becomes a pretty significant requirement for compliance demonstration as well as emission calculations. And then I guess it's not new news anymore, but for those of you with crude oil tanks, if you haven't already looked into the ASTM D6377 method, that is a direct measurement for true vapor pressure that eliminates the RVP, the high-end RVP bias for your crude oil tanks, so you can get a more accurate representation of higher vapor pressure crude oils without having that error, that skewing that happens when you're at the higher range of the RVP test method spectrum. So again, we've already talked about it a little bit. If the TVP, the true vapor pressure at the the worst case product at your worst case monthly temperature exceeds that 11.1 psi threshold, you're going to need a control device and a closed vent system. The interesting thing from the storage tank KB rules is when we look at the definition for maximum true vapor pressure, they talk about things on a monthly temperature basis. So what happens if we exceed 11.1 psi for one day? That may not be that's not directly a KB deviation unless using your monthly average temperature, you exceed that 11.1 psi threshold. So we have some latitude in the representation and definition of maximum true vapor pressure per NSPS KB rules. If you're getting close to that 11.1 psi threshold for one day, though, that typically is an unfortunate harbinger of things to come, and you should be having discussions with your product quality groups, whether that's from a pipeline perspective or a refinery perspective, because it gets very difficult to turn knobs quickly to mitigate temperature, thermal issues, high vapor pressure issues. So again, from a one-day perspective, it's a great check to have, a good thing to keep in mind. It again can ring a bell. But if you have that TVP exceedance for a month, that's when you're exceeding the definition of that maximum true vapor pressure. A one-time, and a quick caveat, your mileage may vary. This is dependent on jurisdictional interpretations. But typically, if you have a one-time TVP exceedance, it's going to be a deviation or perhaps some type of a violation. If you've got a clear path forward for rectifying the issue, for preventing it, it's likely a ding on your permit compliance report. If you begin to have or anticipate having multiple issues, both your friendly regulators may not be as friendly anymore, and it's clearly an indicator that your maximum TVP is no longer below 11.1, and you're going to need to seriously consider those closed vent systems and controls for your tanks. So then we've kind of covered the general record keeping, monitoring, testing. We'll now kind of dive into notifications and reports, which are relatively straightforward compared to some other programs. So we've kind of discussed these already. For an existing tank, if you've got inspection failures, those need to be reported. If you've got an exceedance of your maximum true vapor pressure threshold, that would need to be reported as well. So now for a new tank, if we kind of shift gears a little bit from talking purely the compliance perspective, and we're thinking about what happens when we build a new tank, what does that cover? What does that entail for notifications and reporting requirements? And again, these are found not just in NSPS KB, but they cover the NSPS Subpart A general provisions. There may be state or construction permit requirements as well. Typically, we'll see a construction commencement notification. EFRTs require seal gap notifications before the inspections occur, and those initial reports to be submitted afterwards. There's prior to fill notifications, there's startup notifications, and then there's potentially two, as folks who have gone through construction permitting may know, when a tank is designed and permitted, it may look a little different when it gets built because there's typically something that changes and doesn't get communicated, and there might need to be some as-built notifications submitted as well. Normally, for a tank, if we're talking about a couple extra roof legs or a couple fewer roof legs, that wiggles the emissions a little bit, but doesn't appreciably change the permitting bottom line or anything like that. The bigger challenge is if you permit a 40-foot diameter tank and they build a 50-foot diameter tank, that can be a bit more of a challenge. Or if there's some issues with the product specs or vapor pressure representations, that can create some issues as well. So another key thing to note too, from the NSPS perspective is if your tank is not subject to NSPS KB, we have to be considerate of, are any maintenance projects or construction projects or changes at the facility going to impact our non-KB tanks? And is that going to trigger an NSPS KB by way of reconstruction or modification? And under subpart A, there's different requirements for when a modification or reconstruction notification has to be submitted. And also, if you do modify or reconstruct a tank and you have newly applicable NSPS, if you have a tank that becomes newly subject to an NSPS standard, depending on your state, just that on-paper change of becoming subject to a new regulation may mean you also have to go through permitting as well. So it's important to understand the as-built and as-found condition of your tank and what those changes and how those changes may impact your regulatory applicability for the tank. So what about if you're on a tank for a tour with some new folks at your facility, and you see, a 6 foot by 10 foot pool of crude oil on your tank roof? It's not your annual seal gap inspection. It's not your annual IFRT visual inspection. What do you do? For NSPS KB, it's pretty straightforward to kind of follow that 45-day repair window and notification situation. If it's not a KB tank, you may need to check to your state rules to see if they have any specific programmatic requirements for addressing issues. You may have some permit requirements as well, again, outside of those regulations. And you may have, there may be just the broad interpretation of the general duty clause to utilize good air pollution control practices and make sure that you're doing the right things to prevent increased and excess emissions. So if you see something on your tank, the best practice is, whether it's a KB tank or not, to address the issue, move along, have a nice day, because our friends from the TCEQ, albeit on the emission calculation side of things, if they were an inspector and they showed up and they say, let's look at a tank, and you climb the roof and you see a pool, and then your gauger or your terminal operations person says, oh yeah, we saw that pool there 3 weeks ago. That does not go very well. But if you have an issue, it's been identified, you correct it, you move on, everything works out pretty well typically. So a couple other notes, right? You may remember that very messy, terrible Venn diagram. B1, Max CC, and Max 6B all have some sort of overlap provisions or allow us to look at other regulations, primarily KB, as a way to demonstrate compliance, or if we're subject to KB, rely on that as well. So again, it becomes a little bit of a overlapping spheres of regulations to be mindful of as you evaluate and look at your tank program. So just, again, be mindful that there's not just, unfortunately, one regulation to be mindful of, depending on the operations that you have. So now we'll kind of get perhaps a little bit out of the esoteric regulatory background and start to look at kind of what that means or what's required on our tanks. And an important thing here that we often see helping our clients deal with tank issues is, from the environmental perspective, we have a vocabulary list that is from NSPS KB. It is aligned with AP 42, Chapter 7.1 for emission calculation purposes. And we might call certain deck fittings certain things, but our tanks group, our folks in the field, have different terminology, different meanings. So there's oftentimes, there can be some disconnect. So it's important that from the environmental side, we understand what is required. And then from the operational, actual physical tank perspective, and the folks that are doing the work, we're on the same page, regardless of if we call it a vacuum breaker or a bleeder vent or whatever it may be. So again, we're looking at floating roofs first. There's a couple different types, and I apologize, the color resolution here isn't great, but we've also got the figures from AP 42 as well to help kind of characterize that. Typically, we'll see in internal style floating roof tanks the pan style floating roof. That's a thin layer of steel with an upturned edge that floats on the liquid. We don't typically see the pan style roof on EFRTs because rain, snow, precipitation is going to cause some pretty significant buoyancy issues and cause those to sink often pretty commonly. More often for external style floating roof tanks, we'll see the pontoon style, which have the annular ring of enclosed pontoons around the exterior perimeter of the roof that help provide stability and flotation. We can also see on internal floating roofs an aluminum sandwich panel style. I believe the trade name is Sanborn style floating roof. So that's a thin layer of aluminum, some foam, and another layer of aluminum that floats on the roof. Has a little more rigidity than a steel pan, but really not as much. It also has some deck seam issues that we'll talk about too, but another somewhat common internal floating roof style roof. So again, we've talked about pontoons from an EFRT perspective. There can also be an aluminum skin and pontoon style floating roof on internal floating roof tanks, and that's more of the traditional pontoon, like a pontoon boat. It's got the pontoon on the underside of the roof. Here again, that's the floating roof. There's a roof leg. Here's the pontoons that sit on the liquid, and there's actually a vapor space between the liquid surface and the floating roof itself. There can be double deck hybrid style floating roofs, which are essentially a 2-layer floating roof compartments across the whole roof. That adds some rigidity, some insulating factors when we get to the emission calculations. And it can be comprised of open or closed compartments. And then finally, there's a bulkhead compartment style floating roof. In all of the tanks that I've climbed on and my colleagues have, we have not come across one like this, but it's essentially a pontoon style roof without the enclosed pontoon, which may have some buoyancy issues, but it's a lot easier to tell if there's a leak or a concern with your roof there. There can be some challenges with these annular style pontoons. If they start to leak, it's a little bit hard to tell if you're not monitoring your pontoon maintenance. Anyway, so those are kind of the primary floating roof types that we see that are characterized in AP 42. From a compliance perspective, we want to also understand what our roof liquid interface is. The regulations typically require us to have our roof be in full contact with the liquid surface. But if it's not in full contact with the liquid surface, like the aluminum skin and pontoon style roof, we need to have some type of projection into the liquid surface below the roof. So the floating roof's main goal is to minimize the available vapor space between the liquid surface and the floating roof or the atmosphere. So if we have a roof where the floating roof isn't touching the liquid, we have a vapor space where VOC concentration can build up and it can more readily leak or evaporate into the atmosphere. So to address that, you have to have a projection below the roof or below the liquid level. And I've got a couple pictures of that coming up here. So we talked about the types of roofs. Now we can look at the primary and secondary seals that are used to close off the liquid surface from the atmosphere. So for EFRTs, we have typically a primary seal and a secondary seal, and that's required under KB to have a primary and secondary seal. We'll most commonly see mechanical shoe seals. There may be some liquid mounted seals, and we'll have a few examples of those coming up here. And the secondary seal effectively closes off or covers that primary seal space, so you have a second layer of protection against evaporation losses from your rim seals. For internal floating roof tanks or external floating roof tanks that have a dome on them, from the KB perspective, you've got a couple options. You can have a liquid mounted foam or a liquid filled seal. That is, I've heard it best described as a fancy pool noodle wrapped in a resilient film that kind of allows for a little bit of flexibility as the roof goes up and down. The challenge with those is if your film covering gets ripped or torn, your foam seal can then soak up a whole pile of gasoline or other very flammable or volatile material, and we end up with some pretty significant concerns around safety and or fire or combustion issues. And then you can have two seals mounted above each other or a mechanical shoe seal. So for covered floating roof tanks, you may run into a situation where you just need a primary seal to comply with your regulations, but there may be backed layer or other air quality program drivers that push you to have more than just a primary seal, or you may elect to take one on as an emission reduction activity as well. So what do these look like? A mechanical shoe seal, whether it's on an internal or external floating roof tank, has a couple key features or components. This is from the top side of the roof. This is from underneath. So here's our pontoon floating roof. We'll have some type of a spring or tension device, keeping the mechanical shoe seal flush against the wall and allow for motion as the roof moves up and down. And then in addition to that seal or that shoe closing off the space, we'll have a primary seal fabric here that again has the ability to flex as that roof moves up and down. You can see here it's this dark black fabric material that runs along the perimeter of the rim seal. And from underneath, there's typically a combination of springs and other tension mechanisms to keep the mechanical shoe seal flush against the tank shell. So then I mentioned there can be resilient filled seals. There can be both a liquid or vapor mounted seal approach. And again, when we get to the emission calculations side of things too, we'll see there are some differences in how these seals not just act as a design criteria, but also impact our coefficients for emission calculations. So vapor mounted simply means that the seal is not in direct contact with the liquid, and liquid mounted means that seal is flush against the liquid surface as the tank operates and moves up and down. So then back to the internal floating roof type of tank, we can have a vapor mounted blade or wiper type seal, which is essentially kind of a squeegee that flexes as the tank roof moves up and down. And then for, it can be either more of an elastomeric blade or it can be a foam core coated type seal as well. Again, different manufacturers have different technologies and techniques, but at the end of the day, a wiper seal is a wiper seal. So then when we get to secondary seals, here are a couple different configurations for some of the seals we've talked about. And again, secondary seal is simply another seal that closes off the vapor space or the space above the primary seal. So here we have a primary seal, the resilient foam pool noodle type seal, and then a secondary flexible wiper seal up here. So we've got the primary seal closing off the liquid. The secondary seal creates an additional closure to prevent vapors from escaping the atmosphere. Same thing here. This is two elastomeric blade type seals or wiper type seals, just again, one on top of each other, providing additional emission control from the tanks. Most commonly though, I think, maybe by a quick show of hands, who has mostly mechanical shoe seals on their floating roofs? Or, yeah, I think overwhelmingly for the general industry, we see mechanical shoe seals as the primary seal configuration. And then we can have two types of secondary seals. We can have a shoe-mounted secondary seal, which just sits on the shoe plate of that mechanical shoe seal and provides closure for the vapor space there. You can see the primary seal fabric here. More commonly, what we do see though is a rim-mounted secondary seal, or at least I guess I should say I'm most common with my clients having rim-mounted secondary seals that close off the entirety of the space between the fabric as well as the mechanical shoe, and that helps provide additional emission control and prevent damage from the primary seal fabric from happening. It can be a little bit difficult though, because then when you need to do your, you don't have a good line of sight on your primary seal fabric until you do your 5-year seal gap inspection, or you have odor issues or leak issues or other things that cause you to need to investigate your seals perhaps a little more frequently. All right, so we have gone through the roof, the seals. Now we'll talk about the deck fittings, which is where I think we can run into some of the more common confusion or challenges with tanks, both from an emission calculation perspective and also just working with our groups in the field to understand how to articulate and make sure we're talking about the same things for our storage tanks. So you may recall when we were talking about the floating roof types, we talked about contact versus non-contact. Again, we can see here that there's the pontoon in the background. Here's a stub drain that has, instead of just an opening in the roof here, we have an extension that goes down the angles are a little funky in the photo here, but the projection extends below where the liquid level would be effectively closing off that opening from the vapor space that's created underneath the non-contact floating roof here. Similarly, you can see here for a column support well, there's a extension that provides a protrusion down into the liquid surface so that that opening isn't exposed to the entirety of the vapor space. Okay, so that context aside, we'll now kind of walk through the common deck fittings, understand what the controls or different configurations are, and what those look like with respect to NSPS KB, and then we'll kind of jump into what those look like on the emission calculation side as well. So most commonly, right, we've got access hatches. Pretty much everything we're going to talk about will have a bolted or gasketed configuration to number one, demonstrate compliance with KB, and number two, that affects the emission factor calculations that we do. KB for almost everything requires the covers or lids to have gaskets and some type of mechanical fastening. Additionally, if it's a non-contact roof, there has to be a projection into the liquid. If the roof is in contact with the liquid surface, then we're okay. So again, access hatches, pretty straightforward. They're used to get above and below the roof when the tank is out of service, not typically opened when the tank is in service. For our more analog operators, we have the automatic gauge float wells, which are the more old school style of level indicator for tanks. So there's the kind of a bobber or some buoyant flotation device that sits on the liquid surface. As the tank moves up and down, the gauge wire there feeds into an analog or digital instrument to tell us what our tank level is. And from the air quality side of things, it's important that we have a cover, a seal, or a lid in the closed position with no gap except when in use. And the cover is required to be bolted and gasketed. Interestingly, it's not required to be bolted for an EFRT, but it is required to be bolted for an IFRT. There's some nuance in how KB regulates and explains that stuff. If you go for MAC-WW as an alternative compliance option, you're required to mechanically fasten and gasket your automatic gauge float wells. And just a note too, as I kind of spin through these here, we've got some pictures and examples, but also too, it'll be best to, if you're looking at your tanks, to reference back to the applicable standards and make sure that everything is lined up as appropriate. There we go. Yep, both not specified for KB for an EFRT, but they do require them for MAC-WW. So for our internal style floating roof tanks, the roofs can be either self-supporting or not self-supporting. And for our roofs that aren't self-supporting, we have fixed roof support columns. Tanks can have anywhere between one central column or a dozen or more individual support columns to hold up that fixed roof. And each of those fixed roof support columns create a penetration in the roof and another potential emissions pathway. And so we have to have a flexible fabric seal or gasketed sliding cover, and again, a projection into the liquid if it's not a full contact floating roof. Again, we can see some examples of the gasket material from on top of the roof and from underneath. There's typically a wiper or another more additional gasket material here, preventing any gaps that could allow for an emissions pathway to be created. More commonly on EFRTs, we'll see a gauge hatch or a thief hatch for grabbing samples, for gauging the tanks. There's a couple things to keep in mind. Again, we want to have a gasket on the cover, and the gasket can typically is most commonly going to be somewhere in the lid, but then we also want to be mindful of not having a gap between the flange here as well. That's an important item to be mindful of as well to prevent no gaps or issues there. When we talk about deck fittings in NSPS KB, a good rule of thumb to have is you want to avoid metal to metal contact. If you have a lid and a closure device, you should have some kind of a gasket between there. It's typically required for KB, and also a pretty good practice to have just in terms of minimizing emissions from your tank as well. So then we've got ladder wells. These are common on internal floating roof tanks. For our external floating roof tank friends, we have a rolling ladder well on the top of the roof. That's not an emissions pathway because it doesn't actually penetrate or go through the roof. In the case of IFRTs that have these vertical ladders though, again, we have a roof roof penetration and potential emission pathways that we have to be mindful of. And typically they require a gasketed sliding cover. However, we often see tank builders combine both a ladder well and a slotted gauge pole in a combination deck fitting. So what we do then is, as we see these combination deck fittings, we need to count them as one ladder well and then one slotted gauge pole. And we have to then make sure that the controls required for the slotted gauge pole can integrate with that ladder well as well. And what I mean by that is, in this case, right, we've got the larger slotted pole there. The emission controlling sleeve for the slotted pole has to extend downward and cover not just the slotted pole angle, but cover across the ladder, the rungs to the other side of the ladder well as well, to effectively close off the space that could be created there. And again, there's some gaskets that are required as well. This would be an example of an incorrectly installed gasket that will need to be addressed before the tank goes back into service, because that is much larger than 1/8 inch gap, especially for a new tank. Oh shoot, I jumped ahead of my animation. But yeah, so again, when tanks are constructed, when they're built brand new, when they're coming out of an API inspection cycle, we should often assume that things are in good shape, but that's partly why we have those emptied and degassed inspections before they return to service, to catch things like this, because otherwise these tanks are going to be in service and hard to look at for 5, 10, plus years. So we want to make sure that our deck fitting controls and requirements are addressed before we put it into service for a decade before looking at it again. Another less common one are rim vents that provide a similar service to like a vacuum breaker, but help address pressure buildups when landing or floating a roof. Typically, these require to have gaskets when they're closed. The most common type of rim vent that I've seen is a more enclosed one, so it can be difficult to tell if they have gaskets or not. So you're going to want to work with your tanks group if you have this type of a rim vent to see if they have any mechanical drawings or photos of it disassembled that show, hey, there is indeed a gasket on the pallet or flapper that close off this, close off the cover for this. Because again, if you're an NSPS KP tank, it's required to have a gasket. There can be these older, more manual style vacuum or rim vents that have like a gasket built into the cover or the lid as well. Those are pretty easy to verify, but these internal ones can be a bit difficult and are typically what I've seen on tanks too. So having good manufacturer documentation can go a long way to make sure that they're compliant with any specific regulations. So roof drains have a couple different styles or configurations. The controls are typically a slotted membrane cover where it's at least 90% closed, or just a plug that you can manually open or close. With KB, we typically need to see some type of control on the tank or on the roof drains. They can't just be an open 3-inch hole in your roof, because that's going to be a pretty substantial emissions pathway. And also, right, KB doesn't allow us to have openings into the roof except for when they're operating. So again, the common configuration is just a T-handle plug. Here is actually a sump drain that goes down into a hose system that collects the water and takes it out of the tank without actually exposing it to the product. And here's an overflow roof drain. It's just got kind of a hollow opening, but a similar screw handle cover. Roof legs can be another interesting. I don't know if most people would consider roof legs interesting, but they can be a unique area to consider when you're looking at emission representations from storage tanks. There are several different API documents that talk about roof leg design and spacing, and within AP42, there are several different roof leg configurations that all have different emission factors. So it's really important to, when you're building out a tank in your emission calculations, to make sure you're applying the correct representation for roof legs that are aligned with the type of tank that's being built. So there are internal style floating roof legs, there are pontoon style roof legs, there are center area pontoon style roof legs, and they all have slightly different emission factors. And oftentimes it's pretty easy to match them up based on the roof type or the tank type. But depending on if you're retrofitting a tank with a cover or building a dome style internal floating roof tank, it's just important to be mindful of what those roof leg factors can be, especially if you're in a non-attainment area or other place where you're really trying to be mindful of emissions or minimize emissions through, whatever means that you can. So there's a number of different roof leg configurations, and make sure you know what you're looking at when you're setting up those calculations. Again, we can see pretty straightforward. They have the main purpose is to support the floating roof when it lands. So when that roof goes down, the liquid is drained over the tank. The legs will hold the roof up for an out of service inspection or during a service change or something to that effect. Controls aren't required for floating roof legs under any of the current regulatory programs for storage tanks, but again, depending on back requirements, layer issues, or other things, you may be required to put on socks or gaskets on your roof legs to minimize emissions further above and beyond the primary regulatory requirements. I'd say most commonly we see the roof legs as again going down beneath the roof. On some of the lighter internal floating roof style roofs, we do see hanger wells that are cables that are suspended from the ceiling and support the roof. And have tensioners that coil the cable as the roof goes up and down. Those are treated similar to internal style floating roof legs because they still end up having a penetration through the roof and create a potential vapor space pathway. Another kind of curious one that we see for mostly internal style floating roof tanks is the sample well, kind of analogous to a gauge hatch, but because we can't easily get onto internal style floating roof tanks, the gauger platform, technicians may have a sample cup on a cable, and they'll fish it down into the cone. There'll be again, the resolution isn't great here, but there's a slit fabric seal that generally closes off the opening, but the weight of the sample cup will push through into the liquid. You can grab your sample and pull it back up. Again, these are required to have a 90% cover or slit fabric opening. So then we've talked about a whole bunch of deck fittings. Most perhaps complex or most important to get right from an emissions perspective and a compliance demonstration perspective are the slotted gauge poles or slotted guide pole or slotted anti-rotation pole. Again, we have several different terms for the same thing depending on how the tank is built, who built it, and who's talking about it. The slotted poles create some challenges with the no visible gap standards, and there's a couple different control options or things to consider. So typically we see a wiper on the pole. There needs to be a sleeve or a float closing off the holes in the slotted pole. The cover has to have a gasket. We have to have a projection into the liquid if it's a non-contact roof. There should be a cover cap on top of the pole, or there could even be a flexible external fabric sleeve seal as well. So there's a number of different control categories and requirements, and then kind of a number of different ways to execute those. From a deck fitting perspective, slotted gauge poles can be one of the most significantly high emitting deck fittings, especially if it's uncontrolled or missing a couple of these control configurations. So there's a really important compliance demonstration part with getting your slotted gauge pole controls, making sure they're correct and accurate. But then there's also a significant emissions bottom line piece as well for the slotted gauge pole. So again, we've got a couple different examples of ways these can be executed. So here you can, again, sorry, the projector is not ideal here, but you can see, again, there's the metallic sleeve that extends downward into the liquid, covering up the slots in the pole. Here's maybe a better example, right? Our slotted pole can have these several inch long slots, or it could be just like a 1 inch drill hole. Again, the slots help the product in the tank mix and not get coagulated or stuck in the pole, so that your thermocouples or ultrasonic radar gauges can actually operate better than the slotted pole equivalents. But those slots are great for the operation side of things, not great for the environment emission control side of things, because they're slots that allow a vapor pathway to exist. So to combat that, we can put a sleeve on the underside of the roof that helps close off the availability or open emissions pathways. We can put gaskets and wipers on the pole on the top side to prevent crude oil, gasoline, whatever chemical product you've got from adhering to the clinging to the pole here. We have gaskets between the covers as they're attached. Here's kind of a closer up version as well. We've got a gasket that, or a wiper that extends around the perimeter of the pole. There's gaskets between the covers, and we have just a limited, slot opening on each side of the pole here, as opposed to more open pathways that would allow more significant amounts of vapors to escape through those openings. This was one of the primary drivers behind the Storage Tank Emission Reduction Partnership Program, or STERP program, that I talked about at the beginning of the presentation here, was dealing with this gasket issue in the slotted poles. Conversely, we have unslotted poles that just require a gasketed cover and a pole wiper and a cap on top of the pole. A lot simpler because we don't have those slots in the poles. They look pretty similar too, right? We don't see the slots or the holes in the pole, but there's still gaskets on the different cover areas preventing metal on metal contact. And we can't quite see it here, but there's also the pole wiper that helps close off that gasket area around the pole as well. Stub drains are generally common just to internal style floating roof tanks. They allow for any precipitation runoff or whatever to get off the roof. MACWW requires a closure or cover device. Now, this is a relatively novel technology. There's a little effectively ping pong ball sized ball here, or sphere, that if there was a liquid level buildup on the roof, it would float the ball, allow the material to drain, close back up, and effectively create 90% closure or coverage. So pretty simple solution to a control requirement. KB doesn't require those controls. Another item to be mindful of if you're looking to use the NSPS KB alternative compliance provision and comply with MACWW. If you have stub drains, you'll need to get them controlled if that's something you're looking into.
Yeah, just a side note, you go into find you have those stub drains in order to meet the compliance right away. What we did is we got these fork balls, and stuck a wire through them.
Oh, sure. Yep.
Just bend the ends, and so it essentially functions as the same thing as that. So just if you have those, it's a good alternative. You can do to fabricate up something like that.
That's a good point. Yeah. So if we look back a couple slides back, typically stub drains can have a longer projection in the liquid, or even if it just goes below the roof. Yeah, like Calvin was saying, if we have just a wire coat hanger to keep it in place so it doesn't float away, it provides a relatively quick fix to what can take a long time to fabricate. Another item, the fabrication time, that's a good point. On these slotted gauge poles, if you find yourself with a tank that's not subject to regulation, that becomes subject to a regulation, and you have to get an emission controlling sleeve, those can take an awful long time to fabricate as well. So we'll talk about some modification and reconstruction concerns coming up, but as we go through these deck fittings, if we see things that may be missing or aren't there, it surprisingly may not be a quick fix often. Granted, putting in a new gasket is pretty straightforward, but some of these things can be a little more shockingly time consuming to work up. Okay, so we are nearing the end of the deck fittings, and perhaps the most interesting or perhaps sometimes troublesome outside of the slotted gauge poles, we have our vacuum breakers. So these generally operate when the tank is either being floated or landed to prevent pressure buildup or vacuum buildup from underneath the tank. If we didn't have vents and we were emptying the tank, we could build up enough of a vacuum under the roof and over a large surface area, cause the roof to damage, to flex and break. Or if we were floating the roof and we didn't have vents, there could be some uneven pressure buildup and we could cause the roof to tip and sink, and then we run into all kinds of issues there as well. So these vacuum breakers allow us to have to break the vacuum or to have a vent open for when we're landing or filling a roof. Similarly to everything else, they need to have a gasketed cover But unlike other things, they are allowed to be open only when the roof is being landed or floated. Everything else can be open when you're using it per the regulations, but these can be a bit tricky if they are open when, your crew's up there doing their primary seal inspection or secondary seal inspection, and the vacuum breakers are open. That could be a bit of an issue from a permit deviation perspective if you've got open vacuum breakers when they're not supposed to be open because your roof isn't landed. Typically, they can be fixed back in place. Sometimes the metal baffles here can get kind of stuck on some gunk or whatever, or there's a leg height issue where it's off a little bit and it's popped open. It's an easy fix, but again, per the regulations, we're required to have them closed except for when we're filling or emptying a tank. The gaskets can be a couple different ways. They can be kind of a sandwich material on the top that pinches down, or it can be a gasket along the rim here that when the roof closes, it gaskets itself that way. These are leg style vacuum breakers. There are a couple other more fancy may not be the right term, but pressure actuated vacuum breakers or breather vents that open and close similar to how a rim vent would operate. But most commonly, I think we typically see these mechanical leg style vacuum breakers. So those are the key or the primary deck fittings that exist kind of as laid out in the regulations, as aligned with the AP 42 calculation factors. A couple pictures, if you're newer to floating roof tanks, good. It's a crash course. I'm sure you've got some inspection files that you can look at just to become a little more familiar with them. But the big takeaway here is it's important to maintain an accurate list of deck fittings and controls for number one, compliance purposes. If you're being audited or inspected, and you've got a variety of non-KV tanks or non-max CC tanks and tanks subject to the regulations, there could be some questions around, how do you ensure or have your tanks equipped with the right equipment? Granted, there's also notifications and reports that go in that also assert that, but it's important to know that that you're in compliance with the design standards. You're in design with operational requirements. Again, roof legs and vacuum breaker legs need to be set at the same height, or we're going to run into situations where our vacuum breakers are open when they shouldn't be, or more unpleasant, our vacuum breakers don't open when they should be. So those are some important things to be mindful of, and helps ensure consistency with emission inventories and potential to emit calculations. We want to have the same book of tank math for permitting purposes and compliance purposes, and not have different calculation programs to rectify and explain why is our standing losses different for our emission inventory versus our PTE when they're storing the same product and they should have the same design stuff and they're different, and then it becomes a bit of a challenge to understand what is right, and do we have inspection files? So again, as a best practice, if you haven't, it's important to have a good deck fitting inventory table, spreadsheet, appendix, whatever you want to call it, in a compliance manual that kind of lists out all of your tanks, all of your deck fittings, are they gasketed, bolted, etc. It's good to have that, because as we get into the potential NSPS modification or reconstruction scenario, it's important to know, we had 3 vacuum breakers on the tank, and our engineering group realized that we don't have the right ventilation rate for when we're filling a tank, so we need to add a 4th vacuum breaker. Okay, is that going to trigger permitting? Is that going to trigger an NSPS modification? It's helpful to know that as soon as you can, because there can be permitting timelines and all manner of other items to clear as well. And at the bottom there exactly helps ensure an accurate modification analysis for NSPS purposes. So then just kind of briefly on the storage tanks with closed vent systems, or fixed roof tanks with closed vent systems, we spend a lot of time talking about floating roof tanks because of all of these little nuanced deck fittings, room seal configurations, and everything else. From a KV regulatory compliance side, floating roofs have less direct impacts. You need to have your system designed to collect your vapors and gases. 500 ppm is typically the threshold, and then reduce your VOC concentration by 95% or greater for fixed roof tanks with closed vent systems. When we're also talking about tanks, again, back to our floating roofs, from an operational perspective, we have a couple other things to be mindful of. as well. And that is when we land or fill the tank, how we operate this. And this again is rooted in operational work practice standards, but then also impacts our emission calculations that we'll get into shortly. So directly from the rule, the process of filling, emptying, or refilling shall be continuous and shall be accomplished as rapidly as possible is a bit of a mouthful, but what it means is when you go to empty a tank or fill a tank, you need to get it done in as short of a time frame as possible to minimize those emissions. Continuous isn't super well defined outside of a couple caveats here. Rapidly as possible is not very well defined at all, but there's some discussion around that. So continuous for filling a tank is pretty straightforward, that once you decide to float the roof, you're going to begin to put liquid into the tank until that roof floats. Usually it's a couple hours, depending on the size of the tank, the availability of product, whatever. But what we don't want to run into a situation is you have a tank that's been empty from an API 653 inspection, and it's on high leg roof setting. So it's got about 6.5 feet of vapor space below the floating roof. And you're going to put the tank back into service. You start to fill and the tank begins to fill and you get about 3 feet of product in there. And for some reason you stop. And now you've got 3 feet of product sitting in the tank, or 3.5 feet of vapor space, and you're emitting pretty significantly during that time period for a couple days until you can get more product in the tank to fill it. You can, there can be extenuating circumstances, right, that allow for provisions, but when we fill the tank, we really want to go from start to finish, make sure we have enough product to float the roof before beginning that filling operation. You can start and stop, but can't empty until the roof is floating. So that's, again, you can have some latitude in filling the tank, but it really has to be, as quickly as possible until your roof is floating. But again, filling can be stopped because of some pump failure, or if there were some inventory miscalculations. There is some wiggle room here. It becomes a bit of a jurisdictional basis, a operating philosophy basis. Really the best practice is to, when you go to fill a tank, fill until you can float the roof. Rapidly as possible also is not very well defined. Your enforcing agency has discretion on what's going on here. But again, it kind of comes down to the common sense test of, if you have a tank, you've emptied it to take it out of service, and you've got 2 feet of product left in the bottom, if it's going to sit there for a day or two, a few days, while the cleaning people are mobilizing and staging, that's okay. If you're doing a service change, you have to get the high RVP material out of the tank to refill with the lower RVP material during a seasonal service change. And we're talking about a couple days. Typically, we haven't seen issues or concerns. The issue with regulatory standards comes into play when you have a tank with 2 feet of product that's sitting landed for multiple weeks. That, again, when we get back to what is the intent of the rules are to keep the tank floating, to minimize emissions. And if you've got a couple feet of product sitting there with the roof landed, you're not meeting the intent of the rule. There can be some concerns to deal with there. Another kind of closing caveat is you can remove a tank from service, but you're also not required to immediately degas it. You do have to drain it to puddles to effectively meet the KB standard, but there is some latitude, and it's documented in some of the EPA applicability determinations, that you don't have to degas the tank every time that you empty it, but it does have to meet the drained to puddles standard as discussed in the ADI. And that goes to say effectively that you can have shell clingage and small puddles along the tank floor due to irregularities in the tank floor, but you can't have inches of standing product remaining in the tank. So that is a whirlwind tour through the high-level regulatory background, the design considerations for roofs, tanks, deck fittings, etc., some operational caveats and additional regulatory program stuff. We'll take a break for about 10 minutes, and then we'll jump into the air emissions side of things. So if we could be back at 2:30, that would be great. And if you got, I should have said this beforehand too, but if you have questions, just feel free to bring them up as they come up, or let me know during the break here too. We should have some time at the end for questions and discussions as well, but don't feel like you have to hold on to them until then. So let's take a quick break, and we'll see everybody in a few minutes. of us that have rejoined and carry on here into the air emissions discussion for storage tanks. So, right, we covered a detailed, or at least I should say a high-level background on the regulatory compliance tank design side of things. Now we'll kind of shift gears to quantify the emissions from these tanks based on the tank type and different design considerations, again, focused primarily on AAP 42, Chapter 7.1 as the kind of guiding document for our calculations here. It is important to note that AP 42 is based on several sort of primary source reference documents, the API, American Petroleum Institute's MPMS, Measurement of Petroleum something, that acronym is escaping me, but there's the MPMS documents, Chapter 19, 19.1, 2, 3, 4, all talk about the background and the emission calculations and provide a little bit more context and detail beyond the significant amount of context and detail already contained in AP 42. Additionally, the tank cleaning and degassing losses originally were published in an API technical report document, and most of that has now been incorporated into the latest and greatest AP 42 calculations. So we'll cover all of our kind of primary pathways from storage tank emissions here, and we'll get started. So for fixed roof tanks, there are three primary pathways we'll talk about. Working losses are generated by the throughput in a tank and a upward roof motion. Standing losses are a function of the diurnal temperature changes as the tank heats up and cools down during the day. Vapors expand, the tank breathes or emits. And then, of course, you can clean and degas a fixed roof tank as well. On the floating roof side, we have withdrawal losses, which are based on, instead of the increasing liquid level, the descending liquid level, and the floating roof going down, leaving a thin film of material on the inside of the tank. Standing losses are similar. These are the evaporative losses through the deck fittings, room seals, openings in the roof. We also have, as we were talking about just before the break, landing losses that can include when you land your tank on the legs or refloat it. And you can also clean and degas floating roof tanks as well. It's important to understand the different pathways from the tanks. They're pretty similar, but there can be some subtle differences. Are we talking about inbound throughput for the fixed roof tanks or outbound throughput? Are we talking about incoming or outgoing throughput for the floating roof tanks? So yeah, there's some nuances to be mindful of. For a fixed roof tank, right, our liquid level has nothing on top of it. So as product is pumped into the tank, the level goes up, it displaces vapors through the working loss mechanism. Breathing losses, again, as the tank is subjected to ambient temperature, solar gain, it's going to heat up during the day, vapors are going to expand, it's going to breathe. That will be our standing losses. And then during the night, it cools down, those vapors contract, and the process continues. For a floating roof tank, again, the working or the withdrawal losses now, instead of when we put material into the tank, the liquid level goes up, the floating roof rises and is covering the liquid. When we take material out of the tank, we're drawing down the roof, the liquid level is going down, but we're leaving a thin film of material along the floating roof interior here, and that evaporative loss is the mechanism behind the withdrawal losses. So for a floating roof tank, our major concern is as we're lowering the level of the tank or the throughput that's associated with that drives our withdrawal losses versus the inbound throughput raising the liquid level for a fixed roof tank. Standing losses here, again, are based on temperature, vapor pressure of the stored material evaporating. Even if we have primary and secondary rim seals, not all seals are perfect or nothing is 100%. So we have some evaporative loss through those rim seals. We have evaporative loss through the deck fitting openings, the roof legs, the vacuum breakers, the access hatches, all that stuff contributes to the overall standing losses from the tank as well. And then, of course, when we land the roof, we have a different emission calculation mechanism to address those types of losses. An internal floating roof tank is, from an emission calculation perspective, very similar to an EFRT. However, the bonus feature or the added feature of covering your floating roof tank means you can eliminate the wind-driven loss effects of the rim seal losses and other deck fitting losses. So effectively, it eliminates the wind-driven component of your tank emissions. However, while you get to eliminate the wind-driven component of the standing losses, when you add multiple fixed roof support columns, that adds additional wetted perimeter surface area to contribute to your withdrawal losses. So that's why when we look at the equations in a little bit, for the withdrawal losses, it's not just based on the diameter and size of the tank, but also the number of fixed roof support columns you have in a given tank. A lot of these figures are generally available in AP 42, so they're a little hard to translate on the screen here, but if you have not looked at AP 42 in context or detail, and you're doing tank emission calculations, I won't say it's a compelling page-turning read, but it does have a lot of useful information and context around what these variables are and what everything is used for. So for a calculation approach or hierarchy, there's a couple ways to think about it. I referenced it earlier, the MPMS, Manual Petroleum Measurement. Still missing the S, but that again is the base document for a lot of the background information that populates into AP 42. Unfortunately, the API documents are not publicly available. I think a lot of folks typically have access to them through their companies or organizations. If you're members of API, they're several $100s a piece, so it's not super costly, but it can add up depending on resources and availability. You typically don't need them. What I've found from the consulting perspective is they can be useful in providing really in the weeds context around certain derivations for some of the equations and calculations for really in the weeds minutia questions, but for day-to-day emission calculations, if you know what you're doing, they're not needed, but they can be helpful for context and background, especially seeing kind of the changing additions throughout the years. Those considered official emission source, or official source of emission calculations for tanks and a variety of other sources. And that's where all the calculation methodology is laid out, all the equations, parameters, coefficients, etc., for us to then use. And then how do we use them? There's a couple different ways that you can use them. Historically, Tanks 409 was an option, but that is not an option anymore. With the revisions to AP 42 that occurred between 2019 and 2020, the issues, well, the equations in Tanks 409 just no longer match the current equations in AP 42. So there's already a number of issues with Tanks 409 that made it difficult to use for certain scenarios. Now it's just outright wrong. A number of jurisdictions, I believe TCEQ was one of the earlier ones, saying that, you know, for emission inventories, I think almost as early as 2019 or 2020, we're saying that you can't use the old equations, can't use Tanks 409. Other states have been kind of not as prompt to respond, but are definitely expecting to see things now in the new AP 42 format because that's the preferred calculation methodology. However, we find ourselves in a little bit of a challenge because Tanks was an EPA tool, free and readily available. A lot of tools that exist are off-the-shelf software solutions that have that can be very good, but can also be very challenging to verify or trust, or can be also costly. So that again drives folks to look at developing spreadsheets, which are good because they provide in-house flexibility, but can also be potentially prone to error or issue if not appropriately QA'd, developed, and maintained. From a quick Barr plug, we identified we do a lot of tank work and have developed our Barr tank emission calculation spreadsheet to help kind of fill a gap between Tanks 409 going off to the farm and not having the need for a complex, expensive software solution. So we developed a spreadsheet. It is freely available to folks if they're interested in using it. We'll talk about that a little more at the end. But an important thing to note is if you have a fancy software application doing your tank emission calculations, you need to be very careful about, is it accurate and is it updated to appropriately account for the latest and greatest AP 42 calculation methodology. Tanks 409 had a bunch of known errors, especially with heated tanks and a whole bunch of other things, but really it's not worth talking about anymore because Tanks 409 shouldn't be used. Spreadsheets, like I said, offer a lot of control. You can, I mean, I think we're all relatively spreadsheet savvy in the environmental world. You can manipulate, change, update, do stuff with a spreadsheet more so than we can with a database or a proprietary piece of software. But again, that comes with QA challenges and making sure that your numbers are dialed in and locked in correctly. And of course, that can be difficult to leverage across, an enterprise-wide system or multiple sites. Software applications can be great. They can have good user interfaces. They can generate reports. They can handle large data sets effectively. You can integrate data historian stuff into them. But the emission modules are often an afterthought by the software developers and should be, like I said, very clearly validated against known AP42 correct equations. We were supporting a client that was upgrading their tank farm to a new inventory management solution, and the inventory management solution software was great. It worked well. They were very happy with it. And then for free, they got the emission calculation module that went along with it. And it was about 6 months of going back and forth with them to untangle the correct or incorrect representations for throughput. Throughput was being double counted. There were temperature issues. You had to put in a ticket anytime you needed to change a parameter on a tank. It was not a great look for a supposedly all-encompassing emission calculation tool. So again, not to scare folks off, but if you are using a software tool that's not sort of Tank ESP is a common solution that Rob Ferry and Trinity have used and have marketed and sell, and is focused on tank emission calculations and doing them correctly. Our Barr spreadsheet, we have gone through multiple iterations and QA review and alignment to make sure that those emission calculations are being done correctly. When you're getting a software tool from a software developer that may not have an environmental focus or air quality expertise, there is just a cautionary note to be aware of. And specifically for our regulatory friends, if we do have a black box that we put in numbers and get emissions out, can we show intermediate steps as we get into the calculations here? There's 1,001 equations that we use to calculate tank emissions. Can you confidently demonstrate, how you get from throughput and vapor pressure and tank deck fittings to your total emissions? And do you have confidence in that? And more importantly, does your regulator have confidence in that if we're talking about emission inventories or even permitting purposes as well? So again, AP42, Chapter 7.1, quick, again, takeaways on the calculation methodology. Whatever you use, whether it's a spreadsheet or some software, validating that it's correct and not just taking the vendor's word for it is important. The updates published in AP42 between 2019 and 2020, the most significant changes were to the temperature equations for liquid surface temperature, for bulk liquid temperature, the different families of equations for those tank types. We'll get into those. There was some clear guidance for hot stocks and insulation. The change in emissions for routine operations wasn't significant in that the equations became more accurate, as well, more accurate in that they became more detailed for specific tank types. We didn't see for our clients as we helped them update their calculations a wild change that pushed them into different permit threshold categories for emissions. But it does have a change, and if you have tight permit limits or tight things that you're trying to track, it's important to know that there is going to be some amount of change if you haven't already looked at this to begin with. And that being said, the last thing, the big note, is the inclusion of tank cleaning and degassing emission calculations, and that is definitely a bigger deal for outside of Texas, where folks may not have been as readily tracking or paying attention to those because regulations didn't exist that directly cover those things. Tanks 409, just if you're using it, stop. There's a lot of other options that are more correct and better. So just again, kind of a quick warning there. So beyond the calculations that changed, there were some new coefficients as well that again all trickle down into the calculations. So first of all, there's a brand new meteorological data set. On average, we're seeing a little bit warmer ambient temperatures. So if you're relying on those, that's going to be a noticeable change. The paint coefficients, this is another interesting one. Paint coefficients are now new, average, and aged, as opposed to previously being represented as good or poor. The API documents always had the new average and aged representations in them, but the old AP42 was just good or poor. And so good corresponds to new, poor corresponds to aged, and average is an average of those two. And what that means is without changing anything on your tank, if you are updating your calculations and updating your tank representations based on the new AP42 representations, not overnight, with no appreciable change, you may have a different paint coefficient depending on how your tank is maintained, what your tank paint status is, that could affect your vapor pressure calculations. Not really a huge deal for emissions, but can be a pretty substantial deal for TVP compliance. If you suddenly are very close to that 11.1 PSI threshold, and your tank paint color reflectivity goes from, good to now average, you're going to potentially have a bump up in your vapor pressure. And if you're close to that threshold, that could be a concern to investigate and manage. Additionally, again, this existed in the API documents, but now in AP42, there are two categories of rim seal tightness coefficients. There's, I believe it's called average, which is the same as the tank rim seal coefficients in the old AP42, but there's also a tight fitting category for rim seals. And we have found that the guidance in the AP42 document is not great, and there can be some challenges to assert that you have tight fitting rim seals. So we have not advised clients to use that tight fitting factor because it is going to add another layer of potential burden to confirm, verify, support. One angle could be if you're passing your rim seal or your seal gap inspections on EFRTs, you may have a case to make for using your tight fitting coefficient. But when you don't measure seal gaps on IFRTs, can you in confidence assert that you have a tight fitting seal? Again, some organizational discussions to have if you're interested in it, but I think there's some risk and challenge beyond trying to use that factor. And again, it changes emissions a little bit, but we're not talking about a wild disruption in how those emissions are represented. More work than probably benefit. Additionally, there's the tank cleaning calculations officially incorporated into the methodology and the new temperature calculations, which we'll dive into here. So for a fixed roof tank, right, we talked about working losses, standing losses. Those are our total routine fixed roof loss emissions. Standing losses can sometimes be called breathing losses as well. Here is my one gratuitous figure. We will be diving into the calculations. And the note here is we have less than half of our afternoon left. So I'm going to cover things from a high level, enough to kind of be dangerous and know where the key variables are, but we're not going to dive into all of the equations because I think we'll probably want to go have some fun at some point here this afternoon. So, I mean, I could stand here talking, but let's not get too caught up with there. So anyway, fixed roof tanks. Again, this is the standing loss equation. There's a number of variables, but again, we're interested in the temperature, the vapor pressure, the size of the tank. All of these factors play into it. It's straightforward algebra, but there's a lot of sub equations that take into account essentially the vapor density, the mass of the vapors in the tank that are being displaced during that diurnal temperature change. An interesting note is if you have heated and insulated tanks, that number of days in a month or in a time period a year changes to the number of heating cycles that you have that drive that tank, that temperature change, that delta that creates the breathing losses from that tank. So again, we'll kind of cover some of these factors here that go into the standing losses. So we're curious. We want to know what the vapor space is of the tank, and that's primarily a diameter-driven number, right? We have a big cylinder. What's the volume of the cylinder? We also, we know how big the shell is, what the average liquid height is. We also add the volume of the roof. We get essentially our volume or vented vapor space, which is the amount of space that can be displaced to create our emissions. This is for a cone style roof. There's a different set of equations for a dome style roof because we have a slightly different geometry. You were talking about vertical fixed roof tanks mostly, horizontal fixed roof tanks, right? We flip it on its side. The mechanisms are the same, but instead of we calculate an equivalent diameter, effective diameter, and effective height based on flipping that cylinder on its side and use those in place of the diameter and height in the associated equations. So again, it's important to be mindful of the configuration of the tank and then what are the appropriate diameters and heights to be using. We're looking at the geometry a little bit differently. So then we've got the vented or the vapor space expansion factor. So this is doing that math around that diurnal temperature change or the change in vapor pressure based on the heating cycles. So we're looking at what our change in vapor temperature is, what our change in vapor pressure is. If we have any events, that's what the PB factor is for there, and understanding what that expansion factor is going to be for the vapors in the tank. So here's where we start to get into some of the fun stuff with the changes to our temperature equations. And the biggest one is the fact that almost all of the temperature equations now no longer use a default shell height over diameter ratio, but rather incorporate the specific calculations, the more accurate calculations into the methodology. And what this does is it allows us to be a little more accurate in the tank emission calculation realm. The logic behind it is the computing power of desktop computers has increased such that adding a little bit more complication to our equations is not going to appreciably impact the time or computing power to get them done, and it allows us to be more accurate. So we no longer have a default HS over D ratio, but we can look at our tanks and put in the specific numbers and get more accurate temperatures, based on the different calculations. Again, we see that the alpha is the solar shell paint absorption, and that is, again, I spoke on it earlier, the average versus, or the new versus average versus aged tank stuff that plays into here, so we can see that has an impact on the temperature equations here. Now that was for an uninsulated tank. If we have insulation, we end up with a couple different families of equations depending on the type of tanks that we have. And an important distinction to make here is if you have an insulated tank, it may not be fully insulated. So it's important to understand if you have a partially insulated tank, or if you say your tank is insulated, to understand what the actual insulation configuration is, because that can play into how we represent the temperatures from these equations and the impact of atmospheric or ambient temperatures. So the big one that we talked about from a compliance perspective and are now diving into on the calculation side is the vapor pressure, the true vapor pressure. And for our emission calculations, as well as TVP compliance, we are concerned with the true vapor pressure at the liquid surface temperature. So we have a bulk temperature, which is the kind of common temperature that most people think about. But what we're really curious about is that interface between the liquid surface and the atmosphere, the liquid surface temperature, and that's what we use for the vapor pressure calculations. So here is just the most basic form in AP42. We're looking at temperature in Rankine and pressure in PSIA. This is probably one of the most important equations because the vapor pressure numbers get used in pretty much all the math for all the emission calculations. And the A and B coefficients are vapor pressure coefficients, typically from AP42 or other sources that we can then use to calculate our emissions. It is very important that you're cognizant of what, if you're grabbing vapor pressure coefficients from different sources, what those pressure and temperature units are, because there's a variety of these coefficients published in different sources. that, excuse me, may have temperature in Celsius and pressure in some other metric unit. And it's important that you're apples to apples in terms of vapor pressure coefficients and units. Otherwise, that will skew your vapor pressure calculation. So liquid surface temperature. This is kind of the arguably most noticeable update. Again, we're looking at the HS over D ratio being a critical term for the impact of the ambient temperature, the bulk liquid temperature, and the solar gain on the tank. So all those factors are kind of the three moving parts that influence the liquid surface temperature. What the impact of the ambient temperature, the impact of the bulk liquid temperature, and then the solar gain from just sitting out in the sun. So again, AP42 does still, I mean, it doesn't not allow you to, but if you want to use a default or assume a default ratio, this equation simplifies down to this if you assume the default HS over D ratio. So again, it can be a bit of a algebraic mountain to look at first, but it ends up being not too terrible. But really, we do, and how we specify or set up our calculations, and really the best way to do it is to look at what your actual, HS over D ratio is, especially if you have goofy sized tanks. That's going to skew things a little bit. If you've got tall, skinny tanks versus larger, shorter tanks, it is important to understand what that difference may be. Okay, so bulk liquid temperature. Here, the best guidance, best practice is to use actual measured bulk temperature. If you are a pipeline facility, you may have stuff coming in from your pipelines that are above ambient temperature. If you are at a refinery or a chemical plant, you may have stuff coming off a process unit at an elevated temperature. There are equations that relate ambient temperature to bulk liquid temperature if you're assuming your tank is an ambient temperature tank, which is not a terrible assumption to make, but it's also important to verify or confirm that that's the case. And if it's not the case, then you want to be using those elevated temperatures correctly, because that also plays into your vapor pressure determinations and making sure that you don't have a compliance issue as well as an emission calculation issue. So for bulk, for fixed roof tanks, there's just a simple equation that relates the ambient temperature to the bulk liquid temperature for uninsulated fixed roof tanks. There's still a couple other intermediate calculations that we didn't touch on yet. There's the vented vapor saturation factor, as well as the vapor density factor that again are dealing with converting the concentration of vapor in the vented vapor space into a mass number to get us actual pounds of emissions. There's probably a few other referencing calcs that I didn't touch on here specifically, but again, looking at just this quick smattering of the standing losses for fixed roof tanks, there's a number of calcs that lead up to getting your right numbers. Are you able to, easily audit or verify what those intermediate calcs are before, if you have any questions? And an interesting one that we're seeing more of isn't necessarily driven by regulators, isn't necessarily driven by, environmental department audits or things like that, but we're seeing more questions. Our clients are being asked more questions from their ESG teams as people are trying to understand, audit, and verify that all emissions are calculated accurately, and is there a way to reduce or minimize those? And for tanks, the best that we can do is show and confirm that they're being done correctly. Because again, our tank emissions are vapor pressure, temperature, tank size, kind of difficult to control or turn the knobs on. But again, having transparency in your calculation methods is very important. Probably a theme I will overstate as we continue to go through the stuff here. So we'll shift gears from the standing loss portion of floating roof tanks to now the working loss component. And again, the key factors here are going to be pretty similar regarding vapor pressure, temperature, but we also have one noticeable additional item, which is the VQ, or the throughput moving through the tank that's raising that liquid level. But then some of these other terms, the turnover factor deals with kind of accommodating how active the tank is. And then we have some other factors that address vent settings and the working loss product factor we'll look at too. And the vapor density is the same as the previous equation. For fixed drift tanks, the interesting factor here is, how are you calculating or quantifying your throughput? The easiest way and the most conservative way is to assume that 1 gallon of throughput through your tank displaces the equivalent amount of vapor. However, we want to be mindful that for a fixed drift tank, like I mentioned initially, our mechanism is the upward liquid surface motion, not just necessarily net throughput. So conservatively, if you don't have good tank monitoring equipment or level indicators, you could assume that each gallon of throughput or each barrel of throughput, each cubic foot of throughput corresponds to an equivalent level change. More proactively, what we find our clients are looking to do and we're helping them do is calculate the net upward liquid level change based on level indicators or whatever type of gauging instrumentation they may have in the tank. And that will help us calculate the actual upward motion of the liquid surface. Because in some cases we might have the tank where they're pumping in and pumping out at the same time. So we have that barrel in may not be displacing the same equivalent height as if they're pumping out at the same time. So we want to be mindful of, can we do a better job of more accurately representing that throughput as a change in the liquid height? Pressure and temperature are key parameters throughout all the equations. And then also from a fixed drift perspective, we often see not just a gooseneck vent on these tanks, but some type of a pressure or vacuum vent that impacts the KB calculation, the vented vapor space, or I'm sorry, the vent setting correction factor that can, I hesitate to say, it's an emission reduction tool, but if you have a vent setting on a tank where you're not a pressure vessel per NSPS KB definition, however, you do have a vent setting that is, above and below ambient, that will, as those temperature changes happen, result in, it limits the emission or reduces the impact of the emission calculation. So if you have breather vents, you should be aware of them. You should take advantage of them in your emission calculations. But it's not like a wild silver bullet to greatly reduce your emissions, but it's just another factor to calculate things accurately. So then that is a crash course on the routine losses from fixed roof tanks. When we now kind of switch gears to our floating roof tank world, again, the terms are pretty similar. We've got working losses or breathing losses, working losses or withdrawal losses based on throughput, but now we're shifting to being interested in the outbound throughput or throughput associated with a negative roof level movement, and our standing or breathing losses are a function, again, of just material being stored in the tank. Working losses, also often called withdrawal losses. So for the withdrawal losses, I mentioned this earlier that not only are we concerned with the throughput, in this case Q, but also the number of fixed roof support columns. For all of the losses for a fixed roof tank, those are all essentially vapor-based. When we look at losses for a floating roof tank, the withdrawal losses are actually based on the liquid properties, not the vapor properties. Specifically, we don't see our friend TVP or PVA showing up anywhere here, but rather we're concerned with the withdrawal or the net throughput. And again, net throughput associated with a downward roof motion, a clingage factor, which is based on the product, the average liquid density of the material that's in the tank, a unit conversion constant, the fixed roof support columns, again, to get that wetted perimeter in addition to the internal shell of the tank, and then the effective column diameter of that fixed roof support column. So again, this, of all the equations, is not directly influenced by temperature or vapor pressure. Now, the astute among us do know that density is dependent on temperature. However, in terms of emission calculations for tanks, we typically have an average liquid density profile we use for our crude oil, for our gasoline, for our things like that. So that the fluctuation in liquid density typically doesn't get passed into this equation, but we do want to make sure we're using gasoline density for gasoline, xylene density for xylene, crude oil density for crude oil, etc. So again, throughput level, or throughput, we're concerned with the downward roof motion, the density of the material, the tank diameter. Again, as we have a larger tank, we have less potential downward motion. And then the number of fixed roof support columns as well are important for working losses or withdrawal losses for fixed roof tanks. So now, whereas the fixed roof tanks, we had one breathing loss mechanism or standing loss mechanism, for floating roof tanks, we have three. All of the things on the floating roof can and do influence or create a pathway for vapors, whether it's the deck fittings, the rim seals, or the deck seams. I think that's all my animations. So rim seals, based on your primary and secondary rim seals. Not all tanks are going to have deck seam losses. This is if you have a tank floating roof that's not welded. A welded tank or welded roof doesn't have any pathways. The Sanborn style floating roof, the aluminum sandwich panel style floating roof, anyone that's not welded, that's either bolted or fastened, will have deck seam losses that contribute to these standing losses from the tanks here. So for deck fittings, what we end up doing is calculating a total emission factor for all of the deck fittings on that specific roof. And that's based on individual factors for each individual type of deck fitting, based on, is it gasketed or ungasketed, bolted, unbolted, etc. So we end up looking at the number of deck fittings in a certain group, what those factors are for those individual type of deck fittings, calculating a vapor space function for the month or the year, depending on the time scale we're looking at, getting a molecular vapor weight, using a product factor, and that will give us the deck fitting losses for the access hatches, gauge hatches, etc. So this is kind of the final end-all be-all equation. Like I was mentioning, each deck fitting effectively has its own individual emission factor that gets rolled up into the parent total deck fitting loss factor. The one item to note here for an IFRT versus a EFRT is the KV term is the wind speed correction factor. So if we have an EFRT, it has been empirically derived as 0.7. If we have a covered floating roof, that goes to 0 because, again, the function of those covered floating roofs is to mitigate the wind-driven loss effects. Same thing that obviously the wind speed goes to 0 then too in that term. So anyway, this, and we'll look at these terms in just a second, but each term or each deck fitting has empirically derived loss factors for the type of deck fitting that it is. So access hatches, if you've got a bolted cover with gaskets, you have a KFA of 1.6, and these terms go to 0. If you have an unbolted, ungasketed cover, you have additional terms, and these actually increase pretty wildly for the type of deck fittings that you have. If you ever have to compare deck fittings, a somewhat quick and dirty way to do it is to look at your KFA term is a reasonable leading indicator for the magnitude of a deck fitting, and is it more or less than another one. It's also pretty straightforward to realize that as you add gaskets, bolts, controls, other things, you're going to have lower emission rates from those things. Again, this is from AB42 and provides all the inputs for these based on the different type of deck fittings. So again, from an important concepts perspective for these deck fittings, tank temperature is important. Stored product is important because that feeds into the vapor pressure calculation. You want to have, again, back to what we were talking about earlier, an accurate deck fitting inventory, because if you say you have no slotted gauge poles on your tank, but you actually have 2, that's going to be, again, we're talking a couple 100 pounds of emissions over the course of a year, not like a wild change in perhaps emission fees that you'll be paying from an emission inventory perspective, but you're missing a significant component of your tank that could have issues with emission limits, or just the fact that it's not an accurate representation of what you're reporting, and that has issue as well. So you want to have accurate deck fitting counts so that you can do your calculations correctly and accurately, and is your floating roof covered or not comes back to being an important factor for deck fitting losses. Rim seal losses are pretty similar to the deck fitting ones as well, but instead of being concerned with each individual type of deck fitting, we're concerned with the size of the tank, and then we have, similar to the deck fittings, we have coefficients for the different type of rim seal configurations based on if you have a welded tank or a riveted tank, and what those seal coefficients are that then feed into this equation that are based on developing the losses for a rim seal, or the rim seals on your tank. So what we've seen show up a couple times throughout these equations is the vapor pressure function, and this is kind of an interesting one that was empirically derived or theoretically derived to support the vapor pressure emissions relationships in the corresponding loss equations. And there's some more background in the MPMS documents, but this is effectively the relationship between the ambient pressure and the pressure of the stored material to get our equations to work correctly for the losses. And it's used throughout the equations that we've been looking at here. So now for our fixed roof tanks, here's where we get into kind of the weeds on everything. So for domed and, for internal and domed external floating roof tanks, the liquid surface temperature is approximated, again, based on an equation using our friend, the HS/D ratio, to accommodate the most accurate representation of a liquid surface temperature. And this is because there's significant effective insulation or minimizing effects of the solar gain from the covered roofs. If we look at a external floating roof with a steel peripheral pontoon deck, the single deck center area, so we've got the ring of pontoons around the outside of the deck, and then just a single sheet of steel on the inside, there's a pretty significant weight difference to the ambient temperature versus the bulk liquid temperature. And then almost flipping completely, if we're looking at an external floating roof tank with a steel double deck roof, those coefficients almost effectively flip in that the liquid temperature of the stored material overwhelmingly influences the liquid surface temperature versus the ambient temperature. Whereas in a steel pontoon traditional style floating roof tank, the ambient temperature far out influences the bulk liquid temperature. For context, the old AP42 had one equation for the liquid surface temperature for floating roof tanks, and it had a ambient temperature coefficient of 0.44 and a bulk liquid temperature coefficient of 0.56. So it was much more closer because I think they were averaging the coefficients across all the different types of families of equations to provide one. But now we get this wonderful buffet of options to choose to most accurately represent our type of tanks. So, and that's liquid surface temperature. For bulk temperature, I think we've mentioned this already, measure it if you can, but if you can't, and it's approximately ambient, there are a couple different relationships that exist in the calculation families that relate your bulk temperature based on your ambient. And again, it depends on tank type. And again, that HS/D ratio shows up. And these are all in AP42, but just again, it's not difficult math, but there's just a number of equations to be mindful of that you're implementing correctly as you work across these calculations. Okay, so we've covered rim seal losses, we've covered deck fitting losses. The final loss element for standing losses in a fixed roof tank is the deck seam loss. And this is, again, if you don't have a welded floating roof, there's some assumption that you're going to have evaporative loss going through those seams on your roof as your tank sits with stored product in it. So we have effectively a deck seam loss factor. We have, we calculate the total length of the deck seams that exist on the floating roof. And we use our friend, the vapor pressure function P star, molecular weight, and concentration and saturation factors. And we have, again, there's a couple default representations for deck seam lengths and factors in AP42 to pick what best represents your type of deck fitting or I'm sorry, deck seam representation for your tank, and then that will work back into the calculation, and you'll get your deck seam losses to get added to your deck fitting losses, to get added to your rim seal losses, and now we have our standing losses from a floating roof tank. Okay, so we have covered a number of calculation mechanisms for routine emissions. What is the lowest emitter? What, depending on what you are, if you're evaluating a project, helping folks, scope a project or design a project, what are some important considerations? What is the lowest emitter is often the big question that comes up. And it depends. Backed often favors a covered tank that eliminates the wind-driven effects. But depending on your design criteria and other things, you may be able to show that there's EFRTs that are better performing than covered floating roof tanks because you're adding flexible enclosures onto the slotted gauge poles. You might have roof leg controls or other things, coupled with, when we talk about backed, there's a cost component and technological feasibility component as well. So from the backed angle, we have some opportunity to represent tank emissions or to show that EFRTs can be well-performing tank types. However, if we're in a non-attainment area and we are subject to layer, lowest achievable emission rate, that is always going to be a covered tank as well. So we don't have the necessary ability to, through the backed cost effectiveness, technological feasibility evaluations, show that we can design a low emitting EFRT. So again, right there's outside of layer, there's cost and design constraints to be mindful of, but it may not always be as straightforward a question as is a covered tank the lowest emitting tank or not. A final note too, jurisdiction, as with all air quality things, does matter. There may be some states or locations where even if a traditional backed analysis may show that an EFRT makes sense, jurisdictional standards may dictate that it has to be a covered tank anyway. So just some things to be mindful of. One thing that we have not touched on that fits into the routine losses is flashing emissions. And this is more for our upstream friends, which I don't think anybody here is appreciably on the upstream side of things. That's where we're seeing unstabilized crude from production well areas. It's been effectively, it hasn't been stabilized, so it's got high volatility, light ends, etc. And there's going to be flashing that happens when you go from a high pressure to a low pressure situation. And there are specific calculation models and tools that exist. Promax is one that our natural gas folks often use. You also have to have specific composition data as well, so it's pretty complex. A little bit outside of our purview today, but just wanted to speak to it. AP42 mentions, flashing losses exist and not to forget about them, but doesn't go into a significant discussion around what to do other than using an appropriate simulation tool and appropriate data. Okay, so we have covered the routine emissions, and now we'll shift gears into the non-routine, and that's going to cover the floating roof landing and refilling events, and then also the tank cleaning events as well. So floating roof landings and refillings obviously apply to floating roof tanks and not fixed roof tanks. We have, whenever the tank is in service, the calculations we just talked about are appropriate to use. When it lands, we end up shifting our calculation methodology because the tank effectively becomes a small fixed roof tank because that liquid level has separated from the floating roof. So when does this happen? If the tank is removed from service for an API inspection, if you're doing a service change, if you have to fix a mixer, you might land the tank for a day to pull the mixer, put a new one in. Conversely, when we land a tank to do something, we're typically going to put it back into service. That's when we'll have the refilling emissions. The tank is put back into service from a service change. It's filled for the first time, or you're returning to service after some other event. And we have a different emission methodology because the floating roof is no longer acting as a control device. So we got different methods, and oftentimes this is going to result in significantly more emissions too, because we've got effectively open vents and no passive control. And again, fun graphic, right? When we talk about total landing losses, typically that means both a combination of the landing and refilling emissions as well. Similarly to our standing loss equations, we have different equations based on the tank type. Again, if we have a covered floating roof tank, that's going to mitigate the wind-driven effects. We also have we're interested in what is left in the tank. Is the tank drained dry? Does it have a partial or full liquid heel? That will influence the amount of material available to evaporate, to drive emissions. Effectively, the equations become modified breathing loss and room seal equations. We also calculate limits for a total maximum emission based on the landing events, and that's based on what's left in the tank, whether it has a partial heel or a full liquid heel, or if they're with the drain dry. Those impact the standing loss calculations. I'm not diving into these ones specifically. They're within AP 42, and like I said, we have essentially modified breathing loss and room seal loss equations for the tanks. The filling loss is essentially we're displacing the vapor space below the floating roof. There are two components to be mindful of. There's the arrival loss, and that's effectively what's in the tank that's being displaced. And then there's the generated losses, which are generated by the material going into the tank and saturating that vapor space as well. And these, again, are similar to the fixed roof tank equations that we've already covered. Again, saturation factor, tank type, material stored, or material fill, I should say, impact the overall emissions for these events. So what are the important variables from a landing or refilling calculation? The number of days. Did you have your tank sitting on legs with a foot of product for 1 day, 2 days, a week? Was it drained dry? Again, just a quick, your refilling, your floating must be accomplished as quickly as practicable. The filling loss equation doesn't actually have a time component. It's assumed that when you're filling the tank, you're doing it relatively quickly and you're expelling effectively 1 vapor space worth of material from the tank. Are you keeping records of your landing events, both planned and unplanned? That's getting back to, again, some compliance concerns. We want to make sure we have an understanding of when our tank does land. Do you have any other compliance limits on your non-routine activities? Some folks have emission limits. Other folks have limits on the number of events that they can do when they land at roof. And so then, finally, right, we have the drain to puddle statement. Landing a tank, does not mean you necessarily stop emitting, right? Because you've got these landing losses. But if you can achieve a drain dry configuration, your emissions will drop off pretty quickly. But then even if you're not having a significant emission rate, how long until you're cleaning the tank? Are you going to have odor issues with your neighbor? Again, when you're taking a tank out of service, you want to have a plan in place to mitigate and manage those bottoms if you're not being able to drain the tank completely and then start cleaning right away. Just for context too, when we talk about drain dry tanks, again, we have just a little bit of cleanage left in the tank, nothing in the sump. A partial liquid heel means there's a little bit of material left in the tank and some oil in or around a sump area. And a full liquid heel is there's freestanding liquid across the bottom of the tank. Those configurations get worked into the landing and refilling calculations depending on the type of tank that you've got. Okay, so landing and refilling emissions have been generally around for, I think, since 2006 in AP 42, but the big change, or at least the really new or potentially interesting controversial inclusion is the tank cleaning and degassing emissions. Not controversial from the fact that they should be accounted for, but interesting or challenging in the way that they are to be quantified. And there are 2 main components from the AP 42 representation of the cleaning and degassing emissions. The first is the vapor space purge. So when you begin your tank cleaning process, you're going to turn on some fans or blowers to get things moving out of the tank. And then you've got your continued forced ventilation. As those fans are running, as you have crews in there cleaning the tanks, we'll have continued emissions from that process. So what does that look like? The initial vapor space purge is effectively when you turn on the fans, you have a displacement of highly concentrated vapors. There's not a time-driven component here, but again, we're looking at the vapor space under the floating roof, the temperature, ideal gas constant, vapor pressure, molecular weight, and the saturation factor. So when you turn on the fans, effectively, we're representing an initial displacement of saturated vapor. If you turn the fans off overnight and turn the fans on again the next day for your cleaning process, based on this calculation methodology, you should then have another vapor space purge that occurs because overnight you've had the ability for your vapor space to saturate again. And then as you turn the fans on, you will continue to displace that rich vapor space purge, initially. So then after you turn the fans on, if you leave the fans running overnight or your forced ventilation process continues, we have this equation for forced ventilation. And this is where things get a little bit different or unique compared to the rest of AP42, both for tanks or otherwise. When we think AP42, we're typically talking emission factors, where you have kind of your criteria to use an emission factor multiplied by some type of throughput, and you get an emission rate. And same thing for tanks, albeit a little more complex. However, for the tank cleaning process, we end up with actually a monitored or event-specific variable in the equation. The throughput or the Q factor here is the ventilation rate. The N is the number of days. The T is the other time component. We got vapor pressure, molecular weight of the calibration gas, temperatures, and things like that. But the CV is the measured concentration of the vapor space that's being evacuated from the tank during that venting. And there's a couple different ways that it can be calculated. It can be monitored based on LEL. That was the sort of in the original API technical report that came out. LEL was proposed as an option because it was typically a ubiquitously available measurement that was happening at facilities when tank cleaning was happening, because they had crews going into tanks to clean the tanks. And when there was remaining product in the tank, LEL existed as or you need to do your LEL monitoring for confined space entry. So if you can take LEL and relate that to a concentration, you can get a reasonable mass rate coming out of your tank. You can also do a direct measurement and measure your VOC concentration for what's coming out of the tank as well. But it plays it can be a little bit challenging because LEL is not a very sensitive vapor pressure representation or concentration measurement, whereas if you do VOC monitoring on a ppm basis, you can get better resolution in your data. The ventilation rate plays a pretty substantial factor here. Are your fans moving at 1,000 CFM or 10,000? That's going to have a pretty substantial impact on your cleaning event. Our friends in the refined product industry can typically clean a gasoline tank in a day or two. Our friends that have crude oil tanks can take a week or two or more, depending on the sludge buildup and other issues that may complicate or extend the duration of a cleaning process. And that can really, if you've got a higher volatility material, that can really result in significant uncontrolled emissions. There are some techniques that exist where you can blend in lower vapor pressure material like a distillate or a cover stock or something to mitigate or minimize the vapor pressure of the stored material to help lower the emissions in the cleaning process. But that can also have some challenges as well. So when we're talking about tank cleaning emissions, it becomes really important to understand, do we have any emission limits that we need to be mindful of? And because these emissions can add up pretty quickly. Excuse me. So then if we, some other things to consider, if we stop venting overnight, effectively we have to, based on the calculation methodology, calculate a vapor space purge the next day when the emissions start up again, based on that, on the discussion for those calculations. Additionally, monitoring can be challenging to coordinate. This plays kind of twofold into one, getting good representations for actual emissions, but poses an even bigger challenge from a PTE perspective. If you have a lot of variability in your tank cleaning efforts, it can be difficult to get a reasonable PTE representation because, again, our tank cleaning calculations are based on actual monitoring data. So that can create some challenges. I know in Texas, I believe, right, we have some requirements that are requiring folks to control their tank cleaning emissions or tank degassing emissions to a certain threshold. So you're going to be doing some monitoring in that data collection process. I think most people are familiar with within Texas. As we have been helping clients across other states, though, we find that there is a little bit less savviness or less awareness for the tank cleaning portion of emission tracking and monitoring. So there's, again, that's where the proposal to use LEL data as a surrogate for concentration came up, because the folks are monitoring LEL for safety purposes. Let's double dip and use that to calculate our emissions as well. Some folks bought into that. Other people are still evaluating ways to do a direct VOC concentration measurement for uncontrolled tank degassings, that is. So our emission control is necessary. It depends. Obviously, if you've got regulations or permits that require it, that drives it. What we've seen in our neck of the woods up north is even if emission controls aren't required and emissions are low, odors can be an issue for neighbors, across the fence line, across the way. And so a lot of our clients have proactively begun using controls on tank degassing events to mitigate, potential odor issues with neighbors to the terminals. We have been talking almost exclusively about VOC emissions, but there is, the other thing to be mindful of are the hazardous air pollutant contributions from VOC. And fortunately, perhaps at least it makes it a little bit easier that all of the HAPs that we're typically concerned about from a traditional crude oil or refined product perspective are speciated from our total VOC emissions. So we at least get to calculate the VOCs, and then we don't have to recalculate everything for all these, but rather just speciate them out of our total VOC emissions. So we're talking the BTEX emissions, hexane, these are some of the common ones. There's some speciation data in AP42. There's a little bit more in API's MPMS documents. There's another API document that deals with refinery stream speciation profile studies. There's the refinery emission estimation protocol document. There's an EPA EPCRA industry guidance document that has a number of speciation profiles for various HAPs and other components in various petrochemical and fuels-based streams. SDSs can be a little bit tricky sometimes because, they have a range of materials, but they do certainly exist for more, or they're certainly applicable for more specific or singular chemicals. Industry guidance documents, site-specific sampling, there's certainly pros and cons to all of those for determining HAP emissions. But yeah, so we talk about VOCs. We've been talking about volatile organic compound emissions essentially up until this point, and really all of our standing, working, breathing, withdrawal, cleaning, landing, all of those VOC emissions will have subsequent HAPs associated with them, if not, entirely HAP, right? If we're talking about a benzene tank, our VOC emissions are benzene and our HAP emissions are benzene. But in the case of a gasoline or crude oil, we have some smaller fraction of these HAPs that are also associated with what is in them. Right, we have made it through the calculation zone. And I am going to take a quick break here to rest my voice for a moment. And if we can come back in 5 minutes or so, we've got one last section on sort of tying it all together around air permitting and compliance considerations for kind of tanks in general. So kind of taking everything we talked about and hopefully providing some practical context for you guys to take home. So we'll see everyone back here at 3:45. give folks just one more moment, but we're approaching the home stretch. And like I said before, we'll hopefully tie things together to provide some context around, why the regulatory side of things is important, how that integrates with emission calculations, and some hopefully helpful takeaways to bring home and figure out, where or what you can do to help your tank program. Or keep track of those doing tank calculations. All right, so maybe a good continuation of our final discussion on the calculation side for tank degassing requirements. Give a couple points around, our controls necessary. Requirements may vary by location as well in terms of required monitoring or other things. Much like all elements here, there's a little bit of your mileage may vary. It's important to understand what your permit says, what's required by your local jurisdiction, and whether or not there's anything beyond your permit that may be driving specific controls or requirements for tank degassing events. Additionally, if you haven't already, it's just like roof landings, several years ago, a decade ago, it's important to continue to evaluate including them in your permitting actions as part of your PTE. I think a lot of jurisdictions are continuing to look for or expect to see those tank cleaning emissions in permitting actions for tanks. I mentioned, right, that they can be a large source of emissions if uncontrolled. However, some strategies exist that may help mitigate those emissions, like a diesel flush or distillate flush to blend down that higher vapor pressure material. As we reduce vapor pressure, we theoretically should be reducing emissions as well. That can have some interesting consequences in that you need to certainly have enough of a diesel flush to get that emission reduction occurring. We're typically supposed to be monitoring our tank cleaning events, so we can't just on paper show a vapor pressure reduction, but ultimately we should be then monitoring and having hopefully a connection between our distillate flush, and we see a lower vapor pressure, lower emissions, etc. You can obviously use thermal oxidation to combust the vapors, carbon centrifuge to help spin out the solids and expedite the cleaning process. Depending on how rich the vapors are, some folks have had success using just a sort of a portable engine, internal combustion engine, as a vapor destruction tool as well. But then the big one for this is to, if you haven't already, begin considering and evaluating how you're going to monitor your tank cleaning events. That's going to be the best way to represent them in your emission inventories. And then also, hopefully, as you begin to monitor them, you can get an idea for, do our tank cleaning events have any sort of consistency to them? Can we develop a site-specific type emission representation for our cleaning activities? Or are these just so different that we're going to have to monitor them, no matter what? So some things to be mindful of. Again, so this is kind of the fun grab bag of topics for air quality permitting compliance purposes. So we'll spend a minute here with asphalt or heated heavy oil tanks. This has been kind of a critical area of concern in past enforcement actions and an issue with the older version of AP 42. Vapor pressure coefficients for like number 6 oil and even the asphalt vapor pressure coefficients were underestimating emissions by an order of magnitude or two, and resulted in some facilities incorrectly asserting they did not need air permits when they did. And even though we're talking about relatively small amounts of emissions from these heavier products, because they were using incorrect vapor pressure coefficient data and not correctly accounting for elevated temperatures, there were some pretty significant NOV issues out east for a few terminal companies because of bad data in, really bad results out. So again, we've talked about 1,000 different inputs for tank, tank design factors, deck fitting factors, calculation inputs. But there are real world consequences to the numbers if you're not using them correctly. So kind of a bottom line takeaway is, as you're doing emission calculations, make sure you've got good data, not just for your tanks, but also for your stored products, especially if you're dealing with some of these heavier products that may not have super great or reliable data. And if you are relying on coefficients or old data, make sure you do a good job of running down the background information supporting why it's the right stuff to use. Otherwise, this is definitely a known issue. So if you've got heavy products, you should be making sure you're staying on top of that. One last note too, again, this gets back to insulation. You may recall the calculations we looked at, there were different temperature equations for fully insulated tanks versus partially insulated tanks. It's important to have that represented correctly too, because that can influence your standing losses as well. And again, if we're not talking huge amounts of emissions, but if you're on that bubble between not needing a permit because your emissions are so small and you're not accounting for your standing losses correctly, on top of not using good vapor pressure coefficients, that can run into some, again, pretty serious violation consequences. Tank painting, again, talked about this a little bit up front. The federal regs don't require you to paint tanks, but several state rules do. You may have BAFT requirements that drive you to paint your tanks. You may have local visual standards that require tank painting. An overwhelming majority of tank painting requirements are usually to paint the tank white, because that gives us a better or a lower solar gain, lower vapor pressure, lower emissions. Out west a ways, I believe there are some requirements to paint tanks tan or brown to better blend in with the prairie landscape and things like that. Some of the refineries way out west in the Puget Sound area are required to paint their tanks blue or green, I think, to better integrate in with the natural rainforesty landscape out there. So not always just white, but there can be some drivers. More commonly, if you're required to paint your tank, you're probably going to want to paint it white. So should you paint the tank? Unpainted tanks don't often look great. So there's some optics there. Again, do you want to have nice shiny tanks and be have that positive image associated with you, or do you want the unfinished, unpainted tanks sitting there that are working just fine, but again, we live in a world where there's, optics are important, in addition to the emission benefits as well, and lower true vapor pressures. Some of these are going to be just some rehashes of the earlier points because we covered a lot of stuff. Vacuum breakers are important for operation of the tank, but we want to make sure that they're closed unless the roof is being landed or floated. The mechanically actuated ones often get stuck. You want to make sure that the vacuum breakers can also sometimes open if you don't have your legs set correctly, because you may have a working bottoms set for your tank, and if you got the vacuum breaker legs on high legs and it's misaligned, you're going to have them pop open. Sometimes we may not be able to catch when those vacuum breakers open, but if we see one stuck open, the concern there would be it may be classified as a deviation because you're supposed to be having your vacuum breakers closed at all times, except when you're landing or filling your roof or floating your roof. Let's see here. And then finally, from a permitting perspective, do you need to add vacuum breakers? That again kind of plays into the NSPS modification perspective. If your tank isn't subject to KB and you add a physical change to the roof, that could trigger NSPS KB, or even if your tank is already subject to KB, if you're adding or changing a floating roof parameter, is that going to trigger some kind of construction permitting because it's a physical modification, even if the emission rate is pretty low? So temporary tanks, frac tanks that we talked about way back at the beginning aren't subject to KB. There's no exemption from federal rule applicability for temporary tanks. So that's different than a frac tank, which is a temporary tank, but it's a mobile tank. It has wheels on it. It is designed to move and not be in one spot forever. You can leave a piece of mobile equipment in a spot, and if we kind of step back from tanks and just talk general Clean Air Act air quality permitting stuff, if you leave something in a spot for 12 months, congratulations, your mobile equipment is now stationary. So that's an item to be mindful of. But temporary tanks is more so not just frac tanks, but any other temporary storage that you might bring on site for like a turnaround or cleaning activity. You may not have a specific federal rule applicability from a compliance perspective, but from a permitting perspective, that's where that's more so the note there is you're not exempt from air rules or air permitting just because it's temporary. That can be a challenge in some areas.
Typically, what time frame counts as a temporary?
So that's a good question, and that would be we had some folks when the crude oil prices were pre-COVID stuff having some turmoil. They were trying to figure out a way that they could store more crude oil for a period of time until things became less volatile, and they wanted to bring on these like temporary large, like 40 to 50 foot wide, 10 feet tall, like sort of lined temporary tanks to serve as additional breakout storage. And so that would have been for like a period of 4 to 6 months or a year or something like that. And effectively from a permitting perspective, they may not have had a, I can't remember what the NSPS breakout was, but from a permitting perspective, those would have had to be permitted as effectively stationary equipment on site. From the emissions perspective, not necessarily so much the regulatory compliance side of things. I think that's what the team had ended up concluding with. So there's the temporary part is a challenge when facilities are trying to do something related to like a turnaround or a cleaning or a one-off project where they want to bring certain types of equipment on site. But if it doesn't have wheels or is designed to be mobile, those temporary things typically can't just be you can't do a hand wave at. You have to consider what those emission impacts are as if they were going to be permanent from the permitting side of things. So again, permitting requirements will depend on location. Frac tanks are the one where there's that express exemption, but depending on other things that we've seen too is from a state rule perspective, even though KB exempts frac tanks from applicability, state rule interpretations required frac tanks to be painted white in certain jurisdictions, and they couldn't just get the red, blue, green, whatever generally available ones were, and had to pay a premium to get white frac tanks because that's what the state came back with in terms of that determination. So again, temporary stuff, less from a compliance regulatory perspective and more from an air permitting perspective, doesn't give you a free pass. It requires a reasonable analysis to understand, are you going to trigger potential permitting requirements and how to represent those emissions, even if it's going to be a one-time thing, which can be challenging sometimes. Another technical application for tanks that we haven't touched on too much yet, but does come up, is the nitrogen or inert gas blanket. Typically, we see these on tanks that are storing vegetable oil, tallows, or other things used for renewable fuel production, or or perhaps some very sensitive or material that may be going to a very oxygen-sensitive catalyst or something like that, where we don't want oxidation or O2 contamination to occur with that stored material, so to prevent it from fouling or going bad or getting stinky. The somewhat counterintuitive note is that the presence of an inert atmosphere or blanket on the tank does not impact the AP42 calculations. It prevents oxygen from getting into and oxidizing the stored material, but it does not directly impact or reduce emissions from a tank just because it has a blanket on it. Now, if it's a fixed drift tank and does have an inert blanket, and you've got a conservation vent, pressure vent system on the tank, you can take into account, as we saw earlier in the emission calculations, the breather vent settings, and those can have emission reduction impacts. But the presence of an inert gas blanket itself, right in AP42, they talk about the fact that that does not, in and of itself, limit or minimize emissions. So again, not super common, but we were seeing it more in the renewable fuel sector at like renewable diesel plants and places where they're taking vegetable oil, soybean oil, beef tallow, things like that, and preventing the oxidation from occurring and making the whole place stink, even worse than in some industrial facilities can. Another good one, nod to our TCEQ friends, is short-term emission rate from tanks is not, I mean, a lot of folks do just take their VOCs and divide by 8,760 hours. However, the more appropriate guidance to do short-term emission rate from tanks is to calculate that maximum emission rate, which is typically based on your max pumping rates for filling or emptying the tanks, your warmest months, and highest vapor pressure materials. So there's some TCEQ guidance documents out there. There's API guidance documents as well that reference how to appropriately calculate short-term emission rates from tanks based on those maximum criteria, not just dividing by 8760. Typically, this is most commonly needed for modeling purposes, where we want to have an understanding of what those max hourly impacts are on an hour modeling basis for NACS impacts and things like that. Again, maximum pump rates, warmest months, et cetera, to determine those hourly maximum emission rates. Another fun, interesting one that we've seen some of our clients dealing with is butane blending in gasoline. There can be instances where, right, the EPA or your state regulators can use FLIR cameras or general visible gas imaging to see, where there may be emissions coming from tanks, and we had a client that had a manufactured RVP tank. So they're getting RVP gasoline from a refinery, and then they're also blending at the terminal to get a blended RVP emission, or a blended RVP with butane and gasoline at the terminal. And theoretically, they should have both been RVPX, but when the regulators came by and were looking at the tanks, what should have both been equivalent tanks, they both had working rim seals and floating roofs and no other appreciable issues, there was a very significant difference in the vapor representation coming from that gas imaging. And what seems like was happening is the blended butane blending seemed to have a higher emission rate because, for whatever reason, that blending process was not keeping the butane entrained in the gasoline, and they were actually probably experiencing a higher vapor pressure material in that tank than what they were previously considering. So from a permitting perspective, this is kind of a unique one-off one where we haven't seen this happen too much, but just again around, if you are engaging in any unique or interesting vapor pressure representations, blending, et cetera, are you aware of the broad impacts of things, and is it, is the way that you're representing it, reasonable and accurate to cover, everything that we're talking about, or everything that could be included in the, the eyes of the, your regulators? Is there a stark difference that would seemingly indicate we've got a higher vapor pressure in this situation or not? So again, vapor pressure data is significantly important. We talked about it already from the heavy stock perspective. Another thing to be mindful of is if you're doing testing, what kind of variability do you have? Is there batching? Is there pooling? Is there, are we looking at, you took a sample 10 years ago and have been relying on that for the last 10 years and will do for the next 10 years if nobody says anything? That's not intrinsically wrong if you've got tight production specs, if you have a reasonable level of conservation built into it, that all should not be a bad thing, but you want to make sure that it's still representative, right? It is not good to take a sample and then have things change and not have your data updated to reflect that. Again, RVP, X can be helpful for permitting purposes to represent a maximum threshold, but we do want to consider more dialed in representations for our actual emission calculations. AP42 has a number of vapor pressure coefficients, Perry's Chemical Engineering Handbook, the CRC Handbook, vapor pressure curves developed by test methods or other scientific analytical literature. Again, cautionary note of distillate fuel vapor pressure coefficients from the old AP42. I think we have a slide on that enforcement action coming up as well. Just things to be mindful of. Vapor pressure plays a big part. Another one is the meteorological data. AP42 has updated met data sources. If you're not using monitored met data, you know, you're going to see a little bit of an uptick in your vapor pressure. Not a major concern, but again, if you're kind of riding that razor's edge of TVP compliance, anywhere that you're bumping up your vapor pressure, or I'm sorry, bumping up your meteorological temperature a little bit, bumping up your tank paint coefficient factor a little bit, all of those little things can add up to not a significant increase, but an increase enough where it can cause some concern or alarm around what your TVP actually is, and are you going to have an issue with 11.1 PSI from a compliance perspective. Not a significant issue from emissions, but again, enough small changes can add up to make a bit of a concerning difference. So again, if you haven't updated your calculations for TVP compliance and emission calcs to the newest, latest, greatest AP42, that's the easiest way to tell if there are any issues. So the EPA will kind of get into our enforcement action discussion. I can't say last year because it's 2020, and it's 2022. In 2020, the EPA put out a bulletin titled "The Reminder About Inappropriate Use of AP42 Emission Factors." So they clearly called out tanks 4 and 9 as bad there, not aligned with Chapter 7. They had this covered a bunch of different stuff across AP42, but they specifically talked about 2 key tank-related concepts that we've touched on already today, and that is, are the tank temperatures, are they really ambient, or do the tanks receive hot stock? Because those are two different situations. You can have a tank that might occasionally equilibrate to ambient temperature, but if you're constantly receiving hot stock from the tank and it's getting multiple batches or deliveries per week, per month, whatever your time frame is, you really should consider, again, looking at what is the actual tank temperature and using measured values, or if you don't have measured data, understanding what the more likely real bulk temperature profile is and using that in your emission calculations. And then they also, again, reiterated use actual vapor pressure data if you have it, not the defaults. And if you are using defaults, be aware of risk and concern in those default factors if they're incorrectly applied or they're just bad factors to begin with. So again, enforcement can be pretty significant. Air permit violations specifically are very serious from a public standpoint and a financial standpoint. We see a lot of local interest increasing in engaging with air permitting processes. The NGO groups we are seeing are continually monitoring and engaging more on both large and small projects, which is I think a sign of the readily available information, and engagement is certainly good. But what we do see is with that increased scrutiny, the EPA is continuing to investigate and review and find things. Typically, from an air permit perspective, when there are issues, when there's an NOV, it's in excess of $100,000. There are not small air permit fines if it comes to that. There can be times where you end up with the initial sticker shock of $1 million, NOV, and then there's some negotiating and it gets cut down to $350,000 or something to that effect. But the significance of a 6-figure fine coupled with the publicity around that, it means something pretty substantial is wrong, and it clearly got missed and is not great. So the Sprague and Global Partners cases, these are the 2 situations where they had bad vapor pressure data and didn't have air permits. And I think all of us have some experience in air permitting. About crime number 1 is operating without an air permit, and so that is one of the main drivers that had those costs and had those incidents be so significant. Is I can't remember, didn't have the right type of permit or didn't have a permit because they thought their emissions were so low that they continue to operate as is. If there are issues, again, all the states have different kind of self-disclosure approaches that may be appropriate to help mitigate the issue. If you find a problem, have a plan and fix it. Oftentimes that is seen much more appropriately than letting something sit and getting found in an inspection or other investigation. The EPA continued to do some more research and digging into things. Last year, I think I've got my years correct, there was a guidance memo published titled EPA should conduct more oversight of synthetic minor source permitting to assure permits adhere to EPA guidance. And this one was primarily focused on natural gas sources with specific synthetic minor permits a little west of here. But what the guidance provided a good kind of reminder to folks to understand what are your emission limits, how do you demonstrate compliance with those limits, and is that demonstration sufficient either in how your permit is drafted and written, or is there some disconnect between how you're representing a synthetic minor, compliance representation and what the EPA may or may not be seeing in your permit. So a little bit perhaps more esoteric than not concrete as some of the other topics we've touched on, but if you do have synthetic minor limits or even other non-regulatory driven limits, do the necessary stakeholders know what those limits are if they're asked? How do you demonstrate compliance with them? And is there sufficient detail and documentation in your compliance program? So a lot of what we've talked about today has been assuming your tank is storing gasoline, ethanol, crude oil, diesel. What about the other kind of goofy stuff if you have a reg layer or a slop layer or acids or other non-hydrocarbons? So there's kind of two critical items to think about. And the first is, do the materials form heterogeneous layers? And if yes, so if you've got stratification between water and a distillate layer in like a slop oil or a wastewater tank or a sour water tank, excuse me, you would ultimately look to use that floating layer on top as your vapor pressure and emission calculation representation. That top layer is the one where you're having a vapor pressure representation because of that differentiation. If not, if it is a slop oil tank or a tank that's well mixed or blended, then you can use a weighted average vapor pressure representation. So that's more, again, kind of in the petrochemical world still, or oil and gas world still. From a chemical world, just like with everything else, good vapor pressure data is critical, whether it's an acid tank or some other non-hydrocarbon. All the AP42 equations should still hold and work correctly as long as you've got good vapor pressure data, good molecular weight data. Again, reasonable inputs in mean reasonable emissions out. Let's see here. So the one closing statement is to be mindful of, if you do end up finding questions coming from like your engineers or other folks about what are emissions from a tank or more of a process vessel, or if there's some chemical or physical interaction that's happening that would not allow us to adhere to the ideal gas law basis for the AP42 calculations, you may need to step back and consider what other ways you should be representing emissions from those tanks. But if you have reasonable vapor pressure and chemical and physical properties for the material, and there aren't any chemical reactions or goofy things happening, you should be able to use the AP42 equations without issue. All right, so the last kind of potpourri topic here, API 653 inspections. We have touched on these kind of throughout the discussion today here. There are API standards for in-service and other service inspections, but the one from a tank perspective that I think we're most often interested in is a 653 inspection, that they take the tank out of service, they're doing the integrity measurements, inspections, figuring out if they have to repair stuff, patch things, etc. A lot of times there are some companies that do a really good job of documenting all kinds of stuff in their API 653 inspections, but oftentimes the API 653 inspection itself is not sufficient enough to capture the emptied and degassed or out of service inspection that's required for tanks subject to KB. So when a tank is taken out of service and degassed, it triggers the need for that inspection. An API inspection is an inspection, and sometimes folks think that the the API inspection that's looking at the tank, that's looking at the deck fittings and looking at the rim seals and making sure the tank is still integrity, and sound from an integrity perspective, can cover the AP or the NSPS KB requirements, and oftentimes the documentation in the report itself typically doesn't. So we want to make sure that you've got environmental folks involved with those out of service tank projects to make sure that if you are relying on a 653 inspection, you have environmental folks involved to get the necessary documentation and information captured, or provide detailed training to your tank inspection group to do a tank environmental specific inspection parallel to that or after that API inspection or whenever the tank is cleaned, so that you can make sure all your deck fittings are in good shape, your rim seals look good, and all that stuff. The other thing is for tanks that aren't subject to NSPS KB is being mindful of, as you take a tank out of service, there might be something that's identified, like, again, there's not enough ventilation throughput rates, and you need to add some vacuum breakers, or this tank is so old it didn't have a slotted gauge pull and you want to update it to more modern instrumentation, so they're going to add a slotted pull, but maybe they're going to remove a couple other deck fittings. So do you have a net increase in emissions? Are you going to potentially trigger NSPS KB by way of a modification of an old tank? So the earlier that from the environmental side, you can tie into refurbishment projects to understand if there's going to be any modification reconstruction issues, that's also a good and helpful note to be mindful of. Okay, so this is, I think, the home stretch. Just a quick breakdown on our calculation tool and just some ideas for if you are calculating your own emissions, ways that you could potentially organize or look to account for things. We have, like I said, developed the Barr tank emission calculation spreadsheet as a replacement for AP40 or for tanks 409. We were using it internally for our work and realized that it's a reasonable resource to provide for industry, and it can be accessed via our website. Anyway, so it's an Excel-based tool. We looked at, looking at things from a access database perspective. Again, large data sets tend to lend themselves to being well managed in Access, but not a lot of us speak Access as a common language. And there's also some legacy and stability concerns with Access databases anyway, so kind of dodged a bullet on that one. But anyway, it's an Excel-based calculation tool. It incorporates the latest and greatest AP42 calculations, and we can toggle between the old versions as well for comparative purposes. Less important today because we're kind of well within the new AP42 requirements, but it was a helpful tool as we were assessing impacts for some of our clients. It does, all the emission calculations for fixed and floating roof, heated and ambient tanks, VOC, mixtures of liquids, other stuff. And because it's a spreadsheet, we have kind of the core worksheets locked down, so we can't mess up the calculations. But because it's in Excel, you can add worksheets, you can add tables, and do all the other fun stuff to then take our calculated emission data into other tables or other calculations. The big thing that kind of we found was more helpful than some of the other software we saw was we were able to make pretty useful and human-friendly data entry pages, so that even though we're working in a spreadsheet, it's got a pretty simple user interface for entering your tank properties. Pretty straightforward entries for your deck fittings, the different categories, what type you put in, how many there are. And then you get a list of all your tanks, and it runs about a mile long because of all the different tank properties. One of the more helpful features too was for vapor pressure data. We have our chemical profiles. You can enter in different chemicals with the physical properties, enter in your HAP components. Or if you have a complete speciation, you can calculate your emissions based on 100% speciation, sum of the partial pressures. Or if you have vapor pressure data, you can enter in the temperatures and vapor pressures and calculate constants for a second order polynomial or the Clausius-Clapeyron equation. Again, and then you get a spreadsheet or a table of all that data. We've got data entry for your measured or your ambient temperature if you have site-specific temperature. Otherwise, you can pick your temperature database source from AP42. Then we got just a relatively straightforward data entry page that you can, link up to either your Pi data or data historian for throughput and store product stuff and enter in specific bulk temperatures. And then for landing events and refilling events, again, we've developed kind of useful user forums that help walk through the process a little bit more so you make sure you're entering in your information correctly for those non-routine events. And same thing for tank cleanings. We can, indicate how many days the tank was cleaned, was there vapor space purges, what was the height of the liquid, what was the bottom type, what was our flow rate, concentration, so on and so forth. So what about reports? Tanks 409, for as challenging of a tool as it was, it did have a good, friendly, human readable report that everybody was familiar with and got the job done. We've created similar tables in BTEX that you can print out similar style reports that have all the intermediate calculations. We also can do the API or TCEQ based hourly emission calculations. And then of course we have the non-routine events and routine events and all the intermediate calculations. So we have made it to the closing remarks, and it's nice to see a good chunk of everybody has stuck around. I appreciate that. Key takeaways: deck fittings, tank properties in general, pay attention to the details, have good documentation for what you have and why you have it or why you need it. And then consider what to do about change management. If you're, if you have a bunch of tanks, there's going to be API projects, there's going to be projects that are happening. When something changes out in the field, out in real life, how does it impact your spreadsheet, your table, your tank compliance document? If you aren't subject to KB, consider your modification and reconstruction analysis anytime work is done on a tank. We've talked about modification a number of times. Modification is when you have an increase in emission rate on a kilogram per hour basis as defined by NFPS subpart A. Reconstruction can also happen though if you have a tank and that poor old unfortunate tank has just gone on too long and the roof is Swiss cheese and you have to build a new roof, and that roof replacement cost can be pretty substantial. You could end up reconstructing the tank. The same thing with a floor. Or if a floor is corroding and you have to replace the floor, that can be a pretty significant cost and pretty easily exceed that 50% of the fixed capital cost for your reconstruction analysis too. So if you're not subject to KB, and that's a critical regulation for your tanks, be advised that there could be some issues when you go through these projects. I think I've talked more than enough about calculation tools, and just make sure that you're not using tanks and what you are using is accurate, transparent, and easy to use. Don't forget about tank cleaning and degassing emissions, both from the emission inventory side and permitting if you're not already looking at those. Depending on what you do for your tank program, do you have a compliance document that spells out all the tank stuff that you have to do from a regulatory perspective, from a permit perspective, from a corporate environmental best practice perspective? Do you have all that stuff in one spot? If you don't, a program manual or some sort of additional element into your EMS program or other things can go a long way to kind of prevent brain drain or a lack of knowledge transfer as people move into different positions or move out of the department or move beyond a individual organization. Having taken the time to develop program manuals can go a long way into making sure things continue to get done correctly or making sure nothing gets missed. Finally, right, be aware of unique and challenging and unique or changing conditions. Tanks, especially at refineries, tanks often get kind of they're not the stars of the show, and even though perhaps they should be. And so if you've got a lot of responsibilities, it's important to not pay attention to them because there can be changes, whether it's from, like I said, maintenance projects occurring that are changing things on tanks that might be impacting your emission calculations or other vapor pressure, stored product things. There's, again, just that awareness piece of if you're involved with the tank program, making sure that you've got kind of the ins and outs and everything known, or at least so you can know what you know and know what you don't know. Finally, right, we talked about a whole bunch of stuff. AP 42, Chapter 7.1 is kind of the basis for all this stuff that we've been talking about from the emissions calculation perspective. These are the generally relevant MPMS sections, section 1, 2, 3, and 4, deal with fixed or floating roof tanks, and evaporative loss speciation data. Sections 3 has a number of subparts that actually detail the way a lot of the emission calculations were derived, or emission factors were derived. So if you really get bored on a Friday night, there's an option for some light reading. Or if you want to really just go down a rabbit hole and spend all the money that your organization doesn't have, you could learn how to test for your own site-specific emission factors. I don't think anybody's ever bit on that. So, but again, that's where that methodology exists and where you can find some more information on it. There's a number of other Chapter 19 sections that deal with various parts and pieces of tank program, emission calculation, design stuff, but those are kind of the relevant ones. We're talking about calculation tool. If you don't have something useful, that is an available resource. Happy to talk more about that as well. There's a handful of EPA resources that I'm sure we're all familiar with. There's the EPA Toxic Fuels website, the ADI, Applicability Determination Index. This is, I think the EPA typically publishes these in batches a couple times a year. There's a couple of good ones around reconstruction and modification for storage tanks. There's some about taking a tank out of service and the drain to puddles versus what it means to be in or out of service. The ECFR has had a pleasant facelift the last few months, where it's a little more easy to read and engage with.